you to day 2 of our keynote session. We continue today with another distinguished panel of speakers whose reputation precedes themselves, each with exceptional expertise in their respective field. It is my pleasure to introduce Dr. Avadish Mishra, Associate Professor in the Department of Electrical Engineering and Computer Science at Texas A&M University, Kingsville, USA. He earned his PhD and Master's in Computer Science from the University of New Orleans and his Bachelor's degree in Computer Engineering from Tribhuvan University. Dr. Mishra has published extensively in reputed venues including IEEE, Springer, and Oxford University Press. His research focuses on cyber intelligence, bioinformatics, artificial intelligence, and machine learning. He has led several AI driven projects in areas such as adversarial attack detection, network intrusion detection, malware detection, smart grid security, and protein structure prediction. He has joined us today to talk about enhancing intrusion detection with CNN and CT-GAN synthetic oversampling. May I now request Sir to take over, please?
Thank you so much for that introduction. I appreciate it. And I'll go ahead and get started. So to start with, essentially, as was stated in the introduction, my research is in the area of cyber intelligence and bioinformatics. This is one of the projects out of our lab and was recently published. So I'm going to take you in the journey of network intrusion detection with image-based CNN and CT-GAN, synthetic oversample. To begin with, so I think I can probably skip this slide. As we already heard about myself, and just to kind of emphasize again, I essentially utilize AI and machine learning in cybersecurity and bioinformatics problem. In the cybersecurity or cyber intelligence area, I apply AI and machine learning for adversarial attack defense, intrusion detection, malware detection, and power grid disturbance detection. On the other hand, I'm parallelly taking my research in the bioinformatics area too, and I am engaged in different research problems, and some of these are listed here: torsion angle fluctuation prediction, protein small molecules, interaction prediction, and protein unstructured or structured proteins prediction. I'm a member of ACM and IEEE, and that is a short description about myself. I will go ahead and get started on the details of the presentation outline. So first, I'll just provide a brief introduction and motivation for this work, and then I'll discuss about our method, essentially the data set that we extracted, data pre-processing, synthetic data generation with CT-GAN, and then the tabular data to image conversion, and balancing the data set with undersampling in addition to the synthetic data. And then the CNN-based approach or the model for classification. After that, I'll be discussing about the results. I'll provide an overview of the training and validation performance, confusion metrics and ROC analysis, and the comparative analysis with the state-of-the-art methods. And I will finally discuss about the conclusion of the work and some future direction. So in today's highly interconnected networks, cyber threats are essentially critical concerns as we are more and more connected over the internet. And the conventional approaches for intrusion detection, they utilize tabular data, right, where we have rows and columns, and columns are attributes, and rows are samples, and essentially we have the target level at the end. But just directly feeding, or essentially even the creation of the tabular data, it involves feature engineering, and then furthermore, refining and pre-processing, right? And then feeding it to the model, whereas the models are not able to capture the pattern, right? Um, and they struggle with sophisticated and evolving cyber attacks. In addition to that, the data set that we are using here is NSL KDD data set, and originally this data set is heavily imbalanced, and because of that, it causes models to kind of favor the dominant classes and essentially miss many of the rare attack types, for example, R2L and U2R type of attacks. And in addition to purely, table or feature representation, they often, fail to capture the complex relationships and the patterns that are present in the network traffic. And the convolutional neural networks are very well with image data, right? And so they are pretty suitable for image data set, and we can exploit the spatial feature learning to better separate, the intrusion types. So in this work, we actually collected the NSL KDD data set. We transformed the records that are present in the NSL KDD into images, and then we combined the convolutional neural network-based classification along with the synthetic data augmentation, as well as some undersampling was performed to create slightly balanced data set for 5-class classification of network intrusions. So the method essentially follows as such. First, we gather the data set, then we perform some pre-processings, and I'll outline what those pre-processings are as we go further, and then synthetic data generation with the CTGAN, it's conditional tabular generative adversarial network, followed by tabular to image conversion and class balancing using undersampling, and then once we have our images, we essentially feed that into the convolutional neural network for intrusion detection. So as I said, for this study, we are using the NSL KDD dataset. It's kind of an improved version of the KDD 99 benchmark for the intrusion. We originally collected 43 features, and so original NSL KDD comes with the 43 features. It has different types of data. It consists of categorical data, integer data, binary, and then also the real value features. The approach that we took is we essentially converted the categorical data by using one-hot encoding and converted the total 43 features into 121 features. So only the categorical features were processed through one-hot encoding, right? And we were able to achieve 121 dimensions out of those 43 features. On the table here, I'm kind of displaying different types of attacks: DOS, denial of service attack, probe attack, R2L, U2R, and then the normal category. So there are a total of 5 different categories, right? Total samples 125,973 on the training data and 22,544 samples in the test data. What we can see here is specifically the R2L and U2R. They have a very small number of samples compared to the other classes, and that often causes model to not catch these types, and so our approach for that is to use a generative AI to generate the data, synthetic data, right, to balance the data set. Okay, so I think I have spoken about all of these different points. I'll get to the next slide. So the next step, after collecting the data set, was to apply data pre-processing. And we essentially followed, a couple of approaches for pre-processing. One is encoding. So as I stated earlier, we applied one-hot encoding to all the categorical features to convert them into numerical vector. And then we also cleaned some feature, specifically the SU attempted feature, which essentially contained, it's a binary feature, but then some of the values were, not binary or non-binary, right? So those values, for example, 2, right? These were converted into binary form. Specifically, we replaced all the 2s with 1s. After that, we normalized the data set also. We performed the min-max normalization to normalize the data, and specifically the normalization was performed on the integer features to scale them into the range of 0 to 1. While all the other, real valued features were already normalized, so we did not have to, normalize that particular feature. After that, we also labeled, the 5 classes into 5 categories. We kind of used numerical indicators to indicate those 5 different classes of intrusions. Well, 4 classes of intrusions and 1 for the benign. For the synthetic data generation, as we have to balance the data set, we actually use the conditional tabular generative adversarial network. The CTGAN is available from YData Synthetic Library, and this was essentially applied to generate synthetic data after pre-processing, which involved min-max scaling and one-hot encoding on the KNN trained data set. These are some of the parameters that we utilized to essentially train the CTGAN to produce synthetic data, right? Our batch size was 5,000. Number of epochs, 115. We used Adam optimizer, and learning rate was set to 0.002, and then beta 1, beta 2 values were set to 0.6 and 0.9, which helped us kind of generate synthetic data closely mimicking the real data distribution. And the numerical features that we had in our data set were normalized using the min-max scaling. And as again, it's repeated kind of multiple times that we used on one-hot encoding on the categorical feature. And so we trained the CTGAN to produce around 350,000 synthetic samples. And specifically the synthetic data that we collected for the majority class, the normal and DOS, denial of service, those were actually discarded because we already had enough data in those categories. While we essentially kind of added the synthetic data to our probe R2L and U2R categories. And we added the data into the with the original training set, right? And this actually yielded a more balanced data set, right? And this actually helped the convolutional neural network to learn the pattern both from frequent as well as the rare intrusion types. So okay, so here in this slide, I'm essentially talking about the conversion of the tabular data into the IMES data set. And so we took I think it was 121 features, right? And we converted into 11 by 11 metrics with essentially each feature correspond to 1 pixel in the grayscale. And then we essentially saved it as a .png image and organized our data into training, test, and synthetic folder for the CNN processing. And here's essentially just the image kind of showing that we have tabular data, where we have rows and columns, and then we used a conversion algorithm to essentially convert the data into images. And these are, different samples of images, right? So our images corresponding to different samples or, samples in the data. Okay, so after we added the synthetic data, that was generated using CTGAN, we still had, those majority classes where we had to perform, random undersampling so that we can still kind of balance it out furthermore. And so we essentially reduced the normal samples to 19,000 samples, and then DOS and Prove to 30,500 and 29,500. And then we finally created our data set that was then resaved into, the image form that can be fed into the convolutional neural network. Okay, and so I think I've explained enough about the process for converting the tabular data into the images, and here is essentially the overall approach that we utilized for network intrusion detection. So NSL-KDD dataset consists of the training and test set. We essentially perform some data analysis and also kind of transformation, you can say, right? So essentially, we had our categorical data and we converted it into nominal form using one-hot encoding. The numerical features involved binary, real, and integers, right? And we performed some data cleaning on them. We also eliminated some feature as I outlined earlier, and then we performed min-max normalization of the data. And on the other hand, the number of classes that we had is essentially 5. 4 of those essentially the intrusion types, and then the normal. After that, we went on to essentially collecting the training data using the CTGAN to generate the synthetic data, right? And essentially populate the R2L and U2R, which are the minority classes. After that, converting that into 11 by 11 grayscale image, and then we performed image shuffling, and then afterwards random undersampling, and that's how we got our kind of full data set prepared. After that, we applied the same process on the test data set, converted it into 11 by 11 grayscale image, and then we feed that for testing. Whereas the training data set was split into training and test. We split the training into 80% for training and 20% for validation, passed it to the convolutional neural network. And once we had the model, we tested on the test data set, and finally, that was the model used for detection of intrusion. And this is what is outlined on the text here. So again, I think it is okay to go ahead and skip all those texts. But the next step was to perform the evaluation of the model. So we'll be talking about the results, particularly for training and validation of the CNN model. And then we'll also see how our model performed on the test data set, and some comparative analysis with the state-of-the-art method. So the training and validation performance, as you can see here, I'm presenting the a graph that shows the accuracy over epochs, and it's showing the training and validation accuracy of the CNN model. So the blue kind of curve, it shows the training performance, and the validation performance is the orange curve. And we can see how the model kind of improved significantly after about 10 iterations or epochs, and then it kind of gradually slowly kind of saturated. And same pattern we saw for the validation set as well. And here are some details about the convolutional neural network that was, utilized. We essentially utilized Atom Optimizer, and we had two convolutional blocks, which had, a convolutional layer, and then the max pooling layer and the dropout layer. And these were designed to extract, spatial features while, controlling overfitting. As I think I've discussed about, splitting the training data into training and validation, to kind of validate the model as we are training the model, so that, the model can be generalized. And essentially, here I'm showing confusion matrix, and this shows the confusion matrix on the test data set. So the diagonal elements are showing all the correctly predicted, samples, and the off diagonals basically show the errors in predictions. And it's a multi-class classification problem, so it's slightly complex than the binary classification problem. Okay, and so we can see that the model still struggles for the classification, but we see that many samples were correctly predicted, and essentially later I will show you how did it perform on those underrepresented classes, for example, U2R and R2L. Major success was kind of getting the predictions better for the R2L, right? So that resulted into kind of better performance. Then I'm showing here the performance on the test data set, and specifically the ROC ROC curve, right? Receiver operating characteristics curve. And this is the ROC multi-class, ROC curve, which shows the performance on individual classes. And we can also see the AUC values for each of the class. And we can see that for the majority class, the AUC values are, greater than 95%, and also for the normal class. For the U2R also, the AUC is, 93, but for R2L, it's around 88%. And that is what's kind of described in the text as well here, right? So I'll just skip all of those discussions there. And I would like to draw your attention to the comparative analysis part here, where we are comparing our model with the existing other approaches. And we compare our method with the 4 existing approaches. Compared to the other methods, our accuracy was 87%, which is 6.61% improvement over the existing methods. Precision, we received precision of 87.12%, which is higher than the other reported methods, and we achieved 5.36% improvement respect to the other methods. Likewise, 87% recall with 7.74% improvement, 86.84% F1 score with 12.24% improvement, and then the MCC of 80.80%. Okay, and this is the comparison on the independent test data set. Okay, so if we just look back, into the table that we just saw, we see that our approach that uses CNN with the synthetic data generated using InCITe again actually surpasses all of the existing methods. These are the accuracy, precision, recall, F1 score, and then also kind of improvements that we achieved in the text form. So it's kind of a summary of the previous table, and the method correlation coefficient of 80.80%. And So with the combination that we actually came up with, right, with the CT-GAN, and then conversion of the tabular data into the images, and then class balancing along with convolutional neural network architecture, it actually helped us kind of effectively learn from both the frequent and the rare attack types. Right. So in conclusion, the CNN-based network intrusion detection that uses images seem to perform pretty well, and also the impact of generative AI, specifically CT-GAN-based generation of the synthetic samples that actually helped our model kind of train better, right, and does not kind of just align to the majority class. These were, again, the average percentage improvements over accuracy, precision, recall, F1 score, and MCC. And in addition to that, we also report the tenfold cross-validation score, which is of 96.56%, and the high value of area under the curve, right? It can kind of demonstrates that we achieved a good generalization. And we can rely on these results, and it can be used for the classification of both the frequent and the rare intrusion types. In the future, we plan to explore more advanced imbalance handling techniques, and also integrate the ensemble-based approach, as well as we'll also explore transformer-based architectures to further enhance the performance of our model. Our data and actually the code is available through the link, GitHub link. And I would like to acknowledge our supporters, are the agencies that awarded the grants for us to be able to carry out those research, specifically the Department of Homeland Security. And thank you for your attention, and I would be happy to answer any questions.
Thank you, sir. May I now invite questions from the audience?
Good morning, sir. So my question would be,
Hello.
how can synthetic data quality impact the generalization ability of the CNN model?
Right. So usually when the data set is imbalanced, the model tries to kind of fit more on the majority classes, and by that, when you do not balance out the data set, when you just train the model with the original form where you have not balanced out the data set, the model tend to kind of overfit to the majority classes, right? And the performance of the model is pretty it's better on the training data set, but then if you have the test data set, which is kind of again imbalanced in the similar nature, the performance degrades quite a lot. And so the synthetic data generation and balancing the data using synthetic data generation is a pretty a kind of popular approach currently, as we have these generative AI models that can generate pretty good data set. In one of our study, what we did is we also used generative AI to generate the data, and we looked at how good the synthetic data is compared to our own existing real data. And we found that the generated data were not repetitive, right? So the model did not generate any redundant data, which was good. And so we looked at the samples on each of the classes, particularly specifically, and we did not find any redundancies. And we also find a very good correlation with the synthetic data and the original data. And so it indicates that the generative AI models are able to generate pretty good quality synthetic data sets, right? And as we balance the data, in the case when we have very unbalanced data, the model tend to also kind of capture the pattern well, and it performs well on the minority classes as I displayed in the results. So yeah, synthetic data generation actually helps balancing out the data set. It helps model learn spatial patterns accurately, and then it also generalizes well because we have shown that it also the model can kind of make good quality predictions on the test data set, which is pretty imbalanced.
Good morning, sir.
Good morning.
Question. Why is class imbalance a significant problem in intrusion detection datasets?
Thank you for your question. So it's not just specifically for intrusion detection that it's a problem. It's a problem across the board. Any AI or machine learning application where you have the data which is imbalanced, you'll face similar challenges when you train the machine learning or deep learning models on the imbalanced data. The model tend to kind of overfit on the majority class data because it's training on the similar type of data significantly and often, right? So if you have more number of samples for one particular class, it gets trained on that particular class samples many times, right? And it learns that okay, most of the samples are a particular type, right, or majority class type, and that's why it makes wrong predictions when it is given a test data set. And so it's a problem with the network intrusion detection, particularly the data set that we used, and it's also a problem for any other domain where the original data set is imbalanced.
Any other question? Sir, what percentage of synthetic data is allowed? Like, how much percentage of synthetic data is optimum?
So we can't tell exactly, what percentage is optimum. It's essentially the you would want to, see the ratio of your original, data, right, and try not to like use too much of the synthetic data also, right? Our goal is to balance out the data sets, right? So
Will it affect
um,
accuracy, like if the percentage is higher for the synthetic data and original data is less, so that
yeah.
will be affected or not?
So I would not say it will be affected as long as you have some original data that you can use to train the generative AI models. It generates and it generates good quality synthetic data. We should be good, right? There are many applications where the number of original samples that we have are very few, right? And with those few samples, if we are able to train a good generative AI model and it generates a good synthetic data, then we can have, like, let's say if we have only 100 samples in one particular class, right? And so we generated, let's say, a synthetic data which is 10,000, right? And now with the combination it is 10,100 samples. It's still fine, right? And we just want to make sure that the total number of samples in all of these classes that we have, or all of the categories that we have, they kind of stay similar, right? So if DOS has 45,000, Pro has 11, R2L 995, U2R 65, again normal 67. So you see how significantly imbalanced it is, and that's why we kind of used synthetic data generation to create oversamples for R2L and U2R, and then we also perform undersampling because we have a large number of normal data, right? So we performed undersampling to reduce the number of samples in the normal and then DOS and Pro, right? because we do not want to, kind of add a lot of synthetic data. Like we were able to generate about 35,000 samples using synthetic, data generation. But we don't want to, kind of overload the classes with so many of those samples, right? And I think here, we're showing that, yeah, 350,000 samples were actually generated, right? But we only added some, right? And we also reduced the number of samples from the majority classes, right? To keep it kind of proportional, and not, have one class with the very high number of samples. So there is no, formula, saying, okay, this percentage of synthetic data will be appropriate, right? It's just how you would want to balance your data set out. Somebody would say, okay, why not we increase, the number of samples, and let's say, why not we make all of these samples to 67,000, right? And that may be possible. Why not, right? We can try it out. But then one thing that you should keep in mind is, the time it takes for you to train your model. As you increase the number of samples, in your data set, right, the training time increases, right? And so it's basically a trade-off between how fast you want to train your model, and also, whether you want a lot of training data, and also if the performance is improving, right? Maybe it's worth it to, let's say, train the model for 5 days, right? Instead of just train the model in 2 days. So it's a trade-off, right? Cost is one factor, right? And then how much data you want to use is another factor. How much synthetic data you want to use is another factor, right? So considering all of this into account, to be able to train faster, right? We don't want to kind of overshoot the number of samples in all of these classes. Does that make sense?
Thank you, Dr. Mishra. Thank you for your insight presentation. And I'd like to invite you in person for our next edition for InCITe.
Thank you. Yeah, I will try. It's a little challenging, but absolutely, I would be happy to visit MIT University in person, and specifically for the conference. It would be a good opportunity for me.
Thank you so much, sir. Thanks for your time. Thank you.
Thank you. Have a wonderful day.
I now invite Dr. Ashish Seth, professor at INCITe University, Tashkent, Uzbekistan. Dr. Seth is a distinguished author, researcher, teacher, and consultant with over 17 years of experience in academia. He has made significant contribution to the field of computer science through his research papers, published in esteemed journals. Dr. Seth is actively involved in the academic community, serving on technical review committee and editorial boards, and is dedicated to knowledge sharing through seminars, conferences, and workshops. As an ECM distinguished speaker, he has delivered numerous lectures and training programs, inspiring students and faculty members alike. He has joined us today to talk about Gen AI governance, framework, challenges, and mitigation. May I now request you to take over, sir?
Hello everyone, am I audible to you?
Yes, sir, you're audible.
Okay, good morning everyone. Thanks for the nice introduction of mine. So, first of all, I would like to give my greetings to all the respected members of the conference committee, to all the invited delegates and all the participants. I am thankful to all the conference program organizers, Dr. Hitasa Hastir, and my special thanks to Dr. Richa for associating me with this conference. So today I'll be talking about my views on generative AI. What are the challenges that emerges out of this technology, and then we'll talk about certain strategies for mitigating these challenges. So let's start. Let me show you my PPTs. Is it visible, my PPTs, to you?
Yes, sir. The PPT is visible.
Okay, thank you very much for the confirmation.
You're welcome.
So let's start, and these are the things that I'm going to cover in my talk. So it will start with the definition of generative AI and what does it refers to, and then we'll talk to the challenges that emerge out of this technology. We'll talk about certain mitigation strategies, and then we'll see that how we can control these challenges. We'll address the challenges, and so that we can make use of the real potential of this technology. So generative AI, we call it as Gen AI. So let me start from the very basic definition of Gen AI, and then we'll talk to the uh, challenges that are emerges out of these technologies. So Gen AI at its core, it is a kind of sophisticated computing device, computer system, which is capable of creating new information, new content, and this content may be in the form of text, maybe in the form of audio, video, and these information that we're getting, this is right from the learning that they have got from a huge data set. So to understand how this technology actually works, without diving deep into the complex algorithm, we can think of a neural network, which is basically the main engine behind this Gen AI. It's a kind of digital brain, you can say. Like in the human, we have human brain that basically guide us to take all the action that we are doing, and it also learns from the experience. So similarly, at if you look to this generative AI, it is the key idea is it is uh, made up of, like, neural network is the base behind of its of its power. So it appears to be a kind of architecture, a complex architecture, which is composed of multiple layers, and each layer of this neural network help the system to learn uh, in a step by step way, like we are learning the things in a very definite sequence. So the system will get the information. It's for example, if it wants to learn any about objects, so it will see the shape of the object, it will identify its feature, and then it will understand if some expression is there, if it is a kind of moving object or some kind of motion is attached there, so it can observe all these things. And once when it is trained on this kind of pattern, it is going to generate new information out of it when we write a prompt to get any information out of it. So this is like the Gen AI, the basic introduction. And then let's talk about the challenges. So Gen AI is a very powerful technology. We all are using it, and the potential and the impact of this technology is visible everywhere. We are using it in all the domains and all the industry that has been used. So you can think of if you want to draft any legal document, or if we want to design a new medicine, we are actually taking help of this Gen AI. So this is so powerful, but at the core, this technology is purely operating on some kind of pattern matching things, some kind of statistical probability is also involved there. So fundamentally, it is having no true understanding of the thing. It has no original thought process, and this raises the issue. This raises the challenges. This brings certain risks to all of us because it lacks of the thinking. The original thought process is not involved there. So there are two types of challenges which have been discussed. We are calling it as a technical challenge, and the other you can say as a structural challenge, societal challenge also we are calling it. So technical challenges are like you heard of the term hallucination issues are there, biasness are there, data infringement is there. And when we talk about the structural challenges, this refers to the challenges, kind of governance challenges you can say, that talks about the policy gaps, that talks about the global standards. It talks about the ethical things in the use of Gen AI. It talks about the accountability, the public trust. So there are many issues are there. So when you say that what are the issues that we are having, so we have the issues, and we need to concern about the quality, about data integrity, and the governance is required to control, to decide how we can manage, how we can regulate, how we can align the entire ecosystem with the human values and laws. This is actually required when we talk about the governance. So now, why this has been realized, why this kind of things has been emerging? So this kind of risk has been emerged because of the phenomena that you can see. We can call it as an acceleration gap. So you have also witnessed that the technology is advancing at a very fast pace. Things are coming at exponential things. So the speed at which this technology is advancing and being deployed is so rapid that actually the practical deployment is running significantly ahead of all the necessary ethical assessment that is required, and also all the regulatory framework which is required to control this. So this gap is introduced many real world risk. As I have said that we have gone through the cases of frauds, we have come across the copyright issues, and we need a very comprehensive regulation in place. So we need to think about some mitigation strategies. So what are the risks? So all the risks that we have come across have been categorized or placed into 5 domains that you can see on the screen. So these are the 5 critical dimensions, which is basically impacting the society, impacting the environment, the commerce that we live around. So let me talk about what are the different dimensions of this. So one by one, the very first is actually named as integrity and trust. So it refers to the risk of biasness, inaccuracy. It covers misleading information that we call it the hallucinations. Then the other risk is ownership and rights. So it refers to the legal challenges which is associated with the intellectual property rights, copyright issues, misusing the identity defects that we have already well aware of. Then security and privacy is also other concern, other dimension of risk that refers to the threat of kind of sophisticated cyber attacks, which is being governed by this powerful AI technologies. Then the other risk is the planet and sustainability. So it points out to the substantial environment footprint, which is associated with the training of these uh, uh, huge models. So to train these huge models, to maintain these huge models, it requires lots of energy. So this is also one concern. Then the next is accountability and governance, and it indicates that there is a clear lack of um, uh, kind of legal guidance, and there is a very much need of any comprehensive framework, or you can say as a regulatory framework, which we call as a governance framework. So there is something that has already been in discussion, and we talk about the fairness. So fairness is something that can balance whatever the gaps we have identified, the challenges we have seen. So fairness is something that can address to some extent. So when we talk about the fairness in Gen AI, we are actually interested uh, uh, to cover many of the areas, or you can say we are actually intersecting some uh, big questions that are related to the ethics, on sociology, uh, questions on laws. So if we uh, take a deeper if we want to realize what exactly make the system fair. So many questions you need to ask. Is it something that refers to equal outcomes? It is referring to equal opportunities. Is it talking about the proportional representation? So this is something very subjective, and obviously it cannot be resolved by the AI engineers and the scientists who are working on this generative models today. So Gen AI fairness, when I say, it is a very complex idea that goes beyond not just it talks about being biased, but it is something to think about bringing the exact or neutral representation of diverse group. It is ensuring the fair and accurate representation of those group. Now, this is fairness is something which is actually one of the things that can be realized to address some of the challenges that has been uh, noticed in this technology, but this is not the straightforward. So achieving the fairness in Gen AI is not is not straightforward. It's difficult to achieve for certain reasons. First reason is maybe the training data that we are using. It is biased in many ways. They may be favoring certain group over others, and this kind of biasness in the data is deep rooted, and it is not easy to eliminate. Second, even if we somehow ensure that the training data is not biased, but then we need to come out certain provisions, certain metrics that can ensure that biasness is not there, and if it is there, then how we can evaluate these biasness. What are the provisions we are keeping it to evaluate, to rank it, and to eliminate ultimately. So we have already proposed certain fairness metrics have been proposed. To some extent, they are also helping us to remove the biasness, ensuring the fairness, but it is not a foolproof kind of solution, you can say. So let's move to the. So you can see multiple matrices have been proposed as a fairness matrix, which are having number of parameters. The parameters are not straight. They are actually very complex things to determine in practice. Theoretically, it can be easy to realize, but to monetize this, to quantify these parameters for the evaluation is not that much easy. So let's talk about what are the strategies are proposed so far to address these challenges. So to address the challenges of this Gen AI, we require a multi-layered defense system that combines the advanced technical solutions, and also we need to have a very rigorous procedure control and a regulatory framework along with a mandatory human oversight. Then only we are able to mitigate or address all these challenges. So so let's talk about certain mitigation strategies that have been identified and are used in today's scenario to address these challenges. So you can see here. So the very first is biasness and unfairness is one of the challenges that we have seen. So for this, the strategy must be that we can make sure that we are using a diverse training data. So if we are diversifying our training data, the chances of the harmful representation of these biases is reduced to a very high extent. We need to continuously evaluate our fairness metrics that have been used. We need to incorporate the human checks for at the time of training. Second is hallucination and inaccuracy. So for this again, human oversight must be included. So external verification is suggested here, and human oversight must be made mandatory for any critical applications. So when I say critical application, it is something where the system is going to getting affected to someone's health. It is going to affect to finances. It is impacting to any fundamental rights. So for this kind of application, when GNI is actually used, we need to put a human oversight or a human verification must be there before any action is taken by these kind of systems. Then we have deepfake and frauds are the other challenges. So for this, one prominent solution suggested is the digital watermarking. So watermarking is a kind of it's a kind of technical attack, which is basically include the name of the service provider, and it can be kind of understood by any specific tool. We can go with the adversarial training is also one of the solutions that can address this kind of challenge. Then the next is this privacy leakage. So for this, it is recommended to use a synthetic data set. It's a kind of data set which is not actual true, but it is derived from the actual data set. Data audits are recommended. We need to use the data masking, removing all the PII, that is personal identification information must be removed when we train these models. And then the environmental cost is the also one of the very prominent challenge and issue of out of this technology. So for this, the strategy proposes we need to come up with some very efficient algorithms. So researchers and developers must focus on to develop the optimized model, which requires less energy during both the phases, at the training phase of these models and also at the inference phase when we are using these models. We need to focus on using the kind of sustainable energy sources. We need to focus on using the renewable energy sources. So these are the different aspects which are actually suggested as a mitigation strategy. So technical solution, we have discussed here to address all these flaws, challenges in the in this kind of Gen AI. But if we look for a long-term resilience Gen AI risk, we need to come up with some national policy, some very uh, uh, regulatory frameworks, governance framework we need to come up. And these framework must be able to establish the clear roles, the responsibilities, and also it can be able to do a kind of risk assessment. So already in place, there are certain frameworks have been proposed. The very first framework that has been introduced is by the European Union. We are calling it the European Union AI Act. And it is a very first comprehensive legal framework that governs the use of AI, and it is built on a rigorous risk-based approach. So this approach basically classifying the AI system and based on the severity of the potential harm they are causing to the society. We have identified different categories. So 4 categories have been identified. Based on that, different legal action has to be recommended. So this EU AI Act has a framework that has 4 labels, you can say. The very first is refers to the unacceptable risk, and this must be immediately banned. So this refers to the system that need to be banned because they are generally violating the fundamental rights or the core EU values. And for example, uh, if AI used for doing a social scoring, ranking the citizens based on their behavior, this is something assumed to be a impact on the fundamental right, and the usage of this kind of system must be banned. Then the next is the high risk, which is said to be regulated. It is not to be banned, but need to be regulated. So these are systems which have a high impact on human health, on the safety of the humanity, on the impact of fundamental rights. So if there is any AI system which is used in medical device, or any system which is used for hiring or making selection process. So if this type of things are visible, then strict regulation is required. And also, whenever this kind of system is being identified, so along with the strict regulation, always these systems must be governed by the strict human oversight. Then we have a limited transparency, limited risk is there, which focuses on transparency. So it is the system which is having impacting minimal risk of harm to the humanity, but they have shown some kind of deceptions in their behavior. So again, we need some control parameters, and we need to make sure that it will provide transparency to the users. So developers and deployers need to ensure that end users will always be aware that they are using the AI system. Then minimal risk, which is almost unregulated. Most of the AI that we are using actually comes in this category. So this is something which is uh, providing some challenges, but not affecting directly to human. It is not harming to the human. For example, there may be uh, video games. We can say some activities that is not actually harming uh, to the human health. It is not actually comes that impact on society, the safety of the human, not impacting directly to the society, not violating the fundamental rights of the human. Then that is the 4th category which has been defined here. Then we have explainable and reasonable, or you can say the responsible AI is also being talked of, that can be able to address all these kind of challenges which we have discussed. So we know that AI is getting more and more powerful, and it is going to make a decision in such a way that sometimes we are not able to understand why the machine is behaving in such a way. So there comes a question: how do we trust something that we don't understand? Okay, so we need to come up with answer for this, and to address this kind of thing uh, that can help us to build trust in the technology and also make the safe use of AI. We have there are two kind of things have been introduced: explainable AI and reasonable AI. You can say as a responsible AI. So what is this explainable AI says? So you can think of a system, the organization, let's say in a bank, where the AI system has been used, and you applied for a loan and your loan has been denied. So AI has took the decision. It is just a black box decision to you, because you just know that your loan has not approved without telling you the reason. So this is something very unfair and also irritating as well. So explain level AI is actually here. So if you are using any Gen AI, Gen AI has doing something for you, taking some decision, but it is not able to justify why it has been done. This we need. So this will kind of uh, comes a trust issues. So for this, explainable AI has been actually come in picture here. So explainable AI, when we say, it is representing a set of methods and tools that help us to make AI working transparent. It is mainly help us to answer the question: why did the AI system has making a specific decision for a particular input? So the goal of XAI, you can say, it is basically focusing on transparency. It is basically helping us to develop trust in the system. So transparency means it is helping us to uh, show that how the AI has come up to that conclusion. And definitely, when this kind of information has been provided, it will develop trust in the users about the AI output. So, RAI is also there, and XAI is there. So how they are working together? So they are different uh, in their definition, in their work, but they need to be work together. They are linked together actually. So XAI, when I say, it is a kind of developing a trust and transparency to the AI systems. XAI, you can say, it's a kind of fundamental component. It's a tool or a technique uh, that is helping the system to achieve the RAI. So RAI, responsible AI, is a bigger context, and XAI is something a part of it. It's one of the steps that can help to make the system fully responsible. So RAI refers to the overall goal. It is trying to make the AI to be used safely, ethically. It helps us to generate trustworthiness among the users. And XAI is one of the required steps. It is trying to bring the transparency. It is trying to develop the trust, because it explains the working of the Gen AI models. So they are interrelated, because if we cannot explain why the AI is biased, means it's a failure of the XAI. Explainable AI does not actually work. So we cannot make a system that can be a fair. Means we are actually failure in making a RAI. Responsible AI is actually not reflected there. So, so what is the conclusion? So we have seen many challenges which has emerged out of this technology, though it is very powerful. Challenges are from hallucination to biasness to environmental issues, legal issues are there. But these challenges are actually substantiable. We can control these challenges. and we have the strategies we have discussed. So if we mitigate, if you want to mitigate these challenges, we have to come up with the technical solution that have been identified. We have to make sure that these technical solutions need to be employed in a very systematic way. We need to have a very powerful government's guidelines with us, and we need to train, guide, make aware to all the users and developers of the Gen AI, and ethical issues need to be make them aware. So, in order to finally conclude, we can say that technology itself cannot solve all the ethical dilemmas that it creates. And the ultimate security that we are looking for, it is basically lies not if we just write a better code, but it is also depending on the human judgment, human ethical values, moral values. So need to have a very defined policy structures, and ethics must be imbibed into the users of this AI technology. And we can also like make sure that if we are fulfilling all these mitigation strategies, incorporating all these mitigation strategies into the system, organization can transform all these risks into very manageable challenges, and we can say that the real potential of the this huge technology can be realized in a very effective way. So that's all. So I think we have gone through the challenges, the strategies, and there's need of the governance framework. So if we are able to imbibe all these things very systematically, we can really enjoy and make the use of Gen AI more safer and secure for us. Okay, thank you very much.
The floor is now open for questions. Mic check a little.
Yeah. Good evening, sir. So my question is, how can bias and fairness issues in generative AI systems be identified and mitigated? Thank you.
Okay, so you heard of this one system hallucination, right? Hallucination is a scenario when the system is not actually behaving perfectly and is faking its results. For example, you are using the Gen AI system and it is giving you information which is, for example, you are using some weather forecasting. It is saying that tomorrow will be a heavy rain and there is no rain at all. So that means the system has been biased here. And this has been done because of the data on which it is trained on. So we need to make sure that when we are providing the training to these systems, the data must be authenticated, it must be governed, it must be clean. Then only we can make a control on it. So these are the things that we can do as a human oversight to control over it, and then we can have also some technical solutions for it. We can go for kind of RAG model where we have, which is called retrieved augmented generation, where when we write any prompt to this AI model to do some work for us, it will generate solution for it. But before the solution can be provided to the user, it must be first authenticated from the authenticated data set. So you write the prompt, it generates some data, it is validated from the authenticated data set, and then again it will be uh, kind of executed on your data set, and then the output that you are getting is like more reliable, and there's less chance of biasness. And to address this biasness, there are many metrics have also been proposed, uh, like demographic attributes need to be considered in that metric. Counterfactual need kind of biasness need to be checked. For example, when you are training your data set, providing many demographic attributes, you got some answer out of your query. So let's say you have given some data and let's say you have given some data for job employment and you have provided many input to it, and then you change everything, means you keep everything same, but you change the gender for the same input, and you say that what is the answer of that kind of model. If it is not going to change the answer, that means it is at least not going to biased with the gender. So likewise, many metrics have been proposed, some techniques have been proposed where we can control on this biasness, and also we can identify that up to what extent biasness has been uh, kind of uh, kind of controlled.
Any other questions?
So my question is, what role does data governance plays in managing risk in Gen AI?
What data governance plays a role, right, in the governance Gen AI? You are saying this?
Yes, sir.
So data governance is basically referring to regulations for the use of ethical AI, safe AI, secure AI. So governance is a kind of, you can say, the regulation, the law that will guide you, that will bind you, how to use this AI. So the thing is, when we are using any this Gen AI things, so many uh, peoples are involved. The developer is involved, who is actually looking for the entire architecture of the system. The deployer is involved, who is actually implementing the system, and the user is involved. So governance GI is actually making the framework, is a framework, is a regulation that will hold the responsibility of everyone who is a part of the system. So it's a kind of regulatory guide. It's a kind of legal things which is guiding the fair use of AI. Am I able to answer your question? Am I audible?
Yes, sir.
Okay.
Answer.
Thank you so much for your gracious words, sir. Now we invite Dr. Ankit Agarwal, Research Professor in the Department of Electrical and Computer Engineering at Northwestern University, USA. Dr. Agarwal earned his PhD in 2009 and has established himself as a global leader in interdisciplinary artificial intelligence, machine learning, and deep learning with a focus on high performance data mining for large scale real world problems. He is widely recognized as a pioneer in materials informatics and has contributed extensively across the material science, healthcare, bioinformatics, and social media analytics. With over 200 peer-reviewed publications, more than 17,000 citations, and an age index of exceeding 50, his scholarly impact is truly remarkable. Dr. Agarwal has led or contributed to over 25 major research projects funded by agencies such as NSF, DOE, DARPA, and leading industries including Toyota Motor Corporations. He served as editor in chief of Computer Materials and Quantum Review. Featured among the 2% of scientists globally by Stanford elsewhere. We are truly privileged to have him with us today. He has joined us today to talk about AI for science and engineering, leveraging GPs, XCI, nanocombinatorics, and more. The stage is yours, sir. Over to you, please. Can we have a round of applause?
Morning, everyone. Can you hear me? Thank you. Okay, so we're waiting for the slides, I guess. So in the meantime, I'd like to thank the organizers for kindly inviting me. I've had, I'd say, a rather long association with MIT. I think the first time I was here was back in 2020 for a different conference. I've been able to attend almost every other year or every year sometimes. So I'm always on. Okay. Yes, it's always a pleasure to be here. So thank you for having me. screen possible? Thank you. Okay, so let's start. All right, so today I'll be talking about some of our work for on AI for science and engineering, and the tools, the techniques that we are leveraging are like GNNs, LLMs, XAI, nanocombinatorics, and others. So this I want to acknowledge my team members, collaborators. So I'm a computer scientist by training, but I collaborate extensively with a lot of domain scientists like material science scientists, mechanical engineering, healthcare professionals, medical doctors, and so on. So I want to acknowledge all of those collaborators here, and also the funding agencies that have supported my work over the years. So before I start, a bit of background about the work that our lab does and as a whole is so in this era of big data, I strongly believe that there are these two fundamental technologies of computer science, AI and high performance computing, that need to be integrated more than ever before if you have to solve the big data challenges. So with big data, you need to do data mining, AI and all, and you also need to do it fast. So this integration of AI and HPC, which we call artificial intelligence and high performance data mining, that's what our group specializes in. And then I'm personally very interested in application of these techniques across domains like materials, healthcare, and so on. And today I'll be giving examples from the materials science and engineering domain. So we became interested in this almost 10, 15 years ago. Like I think 2011 was when Material Genome Initiative was announced. So yeah, 15 years ago, and been fortunate to be part of several projects in this space of AI for materials. For example, I'm co-leading the AI tool group at the NIST Center of Excellence, which is a $60 million hierarchical center for hierarchical materials design. Some Air Force projects, DARPA projects, NSF projects, and then lately there has been a lot of interest from industry. A lot of companies have approached us to try to learn and integrate these AI techniques in their workflows. So a couple of projects from Toyota, Japan, that we completed a few years ago. So I like to start with this kind of my pet slide from almost a decade ago now. But if you look at how science and technology has evolved over centuries, we can very clearly identify these four paradigms of science, right? So in the very beginning, science was purely empirical. You look around, you look at the sky, you look at things around you, observe things. So that's today famous as the experimental branch of science. You go in the lab and do experiments, observe, record results, and so on. Then in the 17th century, when calculus was invented, we could take real world phenomena and express them as mathematical laws, like or equations like Newton's laws of motion or laws of thermodynamics. So that gave us the second paradigm of science of theoretical, model based theoretical science. We could try to make mathematical models for real world phenomena. Then over time these equations grew larger and larger. We could not solve them by hand, and then when computers were invented in 1950s, we could solve them on computers and then supercomputers. So that gave us the ability to do simulations. So today we can do weather simulation, climate simulation, material simulation, all kinds of things to simulate real world phenomena and get some predictive power from that. So that is famous as the computational branch of science, simulated science. And here I'm giving examples from some materials domain, density functional theory, molecular dynamics, finite element simulations. If you've heard of these, those are examples of simulations. Now, in the last 20, 30 years, just the sheer volume, velocity, variety of the data that is generated from these first three paradigms, that has far outstripped our capacity to make sense of it. So even as computer scientists, we have become very good at generating data, in storing data, and retrieving data. But when it comes to analyzing the data, our capacity is limited. So we have not been able to keep pace with that. So that's where this fourth paradigm of big data-driven science, where data itself is a resource, in addition to the compute power, in addition to all the physics first principles that we know, just the fact that we have historical data collected, that gives us the ability to extract patterns and then drive insights. So that's famous as the big data driven science or fourth paradigm. And beyond that, AI, machine learning, it's all under this and beyond. So this is easy to see that it's a very challenging problem. Finding needle in a haystack is not easy. And that's what this AI data mining and all is. And I like this example because a lot, because it not only tells us that it is difficult to find the needle. Of course, it is difficult to find the needle, but it also tells us that it is easy to find a wrong needle. What that means is that if we don't really understand these techniques thoroughly, or if we don't understand the data thoroughly, and we just put them together, which is very common nowadays, then we can easily fall into the trap of these wrong needles, because these techniques are domain agnostic. They take in some number, they'll give out some numbers, but if you don't really understand the assumptions behind these techniques, the distributions, the when these techniques work, when they fail, where the data is coming from, what kind of noise it has, and we just blindly put the two together, we will get some model, no doubt, because again, garbage in, garbage out, but then we'll not be able to use it, or it will not have utility. So this false needle thing is very, very common and a big risk in this domain, and we'll come back to this point later. So what is AI? Ability of machines to perform tasks that normally require human intelligence. And I'm sure you've seen these kind of diagrams where deep learning is a subset of machine learning, subset of AI. And there are different ways you can classify these techniques. I particularly like weak, strong, and super. And interestingly, everything that we have today is an example of weak AI, which means we can build an AI system which is as good as, even better than humans for one particular task. Maybe autonomous driving, maybe playing chess, maybe playing Go, or some particular robot which is doing a particular thing. But it cannot do everything the human does, which will be strong AI, and super AI is beyond that. So all the sci-fi movies you see where AI takes over the world, that's super AI. And fortunately, that's not happening, at least anytime soon. Although, if you are following this field, I'm sure you are aware, there have been a lot of voices, especially in the last few years with the advent of generative AI, that AI is becoming too powerful, too fast. And we need to kind of scale it. We need to regulate the advent of it, like how quickly it is becoming powerful. And there are concerns that, it can be misapplied. Of course, that's one thing, but maybe it can gain control and all, that's a strong super AI kind of thing. So that's a different topic altogether, but I think it's important to keep that in mind, that we need to be able to use this technologies wisely. And we'll again come back to that later if we have time. So what is machine learning? Field of study that gives computers the ability to learn automatically from without being explicitly programmed. So you don't say that, okay, if you see this, do this. If x greater than 4, then do this, do that. Not like that. You just give it data, and it learns patterns from that. So it's easy to see that the performance of these algorithms improve as they're exposed to more data. And these concepts have been very old. They were discovered invented back in 50s, again became popular in 80s, but there has been an AI winter every once in a while. So they have always been hungry for big data and big compute. And only recently we got this capability to collect huge amounts of data and huge amounts of compute power. So that's where deep learning comes in, because that's also neural networks were invented back in 80s, or even before that actually. In 50s there were some hints of that. But only recently we got this big data and big compute, and that's why deep learning has taken off the way it has in the last, I would say, 15 years. And today, that's what drives most of the AI innovation, deep learning algorithms. And they are in different architectures, these models are built. So you can see that we already saw that big data and big compute is what is needed for a good deep learning model. Architecture search and interpretability are also open problems. So these are all challenges. But the advantages are far greater. And the biggest advantage is that it's feature engineering free. So we can now just give it raw data. It can build models from raw data by extracting features and hierarchy of features by itself. And these are different kinds of model architectures: fully connected network, convolutional neural network, very popular for images, a graph neural network for things like connected things like atoms and bonds in material science. Generative adversarial network, a kind of generative model where you train two models, generator and discriminator, and they try to beat each other till they become both strong until Nash equilibrium, and then the generator can be used to generate realistic fake data. So all these deep fake technologies are based on that. And then last few years, transformer architecture is the most widespread, most popular that has come up. So the T in ChatGPT stands for transformer, right? So it has this multi-headed attention mechanism that makes it more interpretable and scalable and accurate and also on. So coming to the use case here, we are interested. Like my work mostly last 10 years has been focused on AI for materials. So how can AI help in advancing material science? So again, I'm not a material scientist, but I have collaborated a lot with them. And if there's one thing I've learned, is that everything in material science depends on these PSP relationships, so processing, structure, property, performance. And this is very similar to bioinformatics. My PhD was in bioinformatics like 20 years ago. And then there everything depends on PSP relationships. So sequence, structure, function relationships. So we have a DNA sequence that gives rise to protein sequence that gives rise to protein structure and protein function. So pretty much entire bioinformatics is around those, understanding those linkages. So similarly here in materials, we have processing, structure, property, performance, and the science goes from left to right. So you can understand that the way you process a material will determine what the structure of the material is. The structure will determine what the property is, property will determine what the performance is. So cause and effect of science relationships goes from left to right. So processing is the cause, structure is the effect. Engineering is always the opposite. So goals and means. So if my goal is high performance, the means to achieve that goal is to work on processing, work on composition, work on structure. So they're always kind of complementary. So what can AI do? AI or materials informatics, it can help us generate these forward models for the science question, for prediction, where we can express the property of a material as a function of representation. So if I can learn this function f, it can take some representation, some combination of processing, composition, structure, and it can give me the property instantly instead of doing the actual experiment or simulation. So that's how AI can be used to build the forward predictive models. And these models are always fast, but if they're also accurate, and that depends on how we make them, they can help in the inverse relationship as well. So inverse is engineering relationship of goals and means. So here we are trying to discover mostly the best material. So the goal is to discover the best material with the best performance and all, and we have to look at the space of possible materials. The space of possible materials is huge, right? Infinitely possible materials. You can take different elements and different ratios, different structure, and so on. So if you have a very good fast and accurate forward model, you can search that space very fast. If you have, let's say, millions or billions of combinations, you cannot do all the experiments. But if you have a very fast forward model, you can kind of convert that set to a ranked list. You can prioritize that, okay, these are more promising materials that I should evaluate. So I explain all this in this perspective article from 10 years ago. It's getting very good readership with over 1,000 citations already. So please feel free to take a look if you are interested in more details. Another way to look at this, I already told you that there is forward and inverse problems. There are two fundamental kind of problems of prediction and discovery. So again, prediction is given the material, what is the property? And inverse modeling is opposite. Given the property, what is the material, right? So it's exactly complementary. The challenges for forward modeling I see is small and big data. Sometimes we have very small data for a particular problem, maybe 100,000 data points. So that's a challenge because just not enough data to make a good model. And sometimes we have big data problem that you have so much data, the quality control may not be there, or it may take a long time to build a single model. So we may not be able to get the best model quickly. So those are the two fundamental challenges in the forward modeling task. For inverse modeling task, it's not really a question about data, but design space. As we just discussed, the space of possible materials is huge, right? So incidentally, it is always big. It can never be small. So if let's do a quick back of the envelope calculation. If we, let's say, take all the elements in the periodic table. Folks here remember periodic table, right? There are about how many elements on the periodic table right now? About, yeah, so let's, for calculation's sake, let's say 100. And let's say we take ternaries. So ternaries means the 3 elements at a time. Let's call them ABC. A can be sodium, B can be chlorine, and so on. So ABC, so how many possible combinations of these ABC? 100 each, right? So 100 times 100 times 100, assume overlapping for now. So about 1 million combinations, right? And then if you remember that they can occur in different ratios, right? Fe2O3, FeO, they are not the same. So it can be AX, BY, CZ. So if we take all the possible stoichiometries or the ratios, it can increase another few orders of magnitude. So from million, it can become billion, trillion, or something like that. So I'm calling it about 10 to the power 10 combination. So that's big, but that's still not huge. You can still take an AI model and scan everything. If I take an AI model and scan 10 to the power 10 combination, it will hardly take me an hour, and I can parallelize it because these models are very fast. So I can take all those 10 to the power 10 combinations and rank them, and then only do experiments or simulation on the top ones. So that's somewhat easier. But if you go to microstructure space, remember processing, structure, property, performance. There, if you take a very simple microstructure, let's say we just take a square of 20 by 20 pixels. So how many pixels there? 20 by 20 pixels. How many pixels in the square? 400. And let's say each pixel can only be black or white, just two possible values. So how many possible squares? each pixel can be black or white, right? So let's say the first one is, so let's say all are white, that is one microstructure. Then the first one is black, rest are white. Then the second is black, and then maybe few of them are black. So there are actually a lot more. So any guesses? 2 to the power? Exactly. So there are 2 to the power 400 combination of a very, very simple square, which only has 400 pixel, and each pixel can have only 2 values. Real microstructures are much more complex, 3D, and many more combinations, many more possibilities, and so on. But this 2 to the power 400 itself is greater than 10 to the power 100. If you take the log and convert, you'll see. So this is such bigger number that even if we have the best AI model, which takes nanosecond, picosecond, you cannot scan everything, right? It will take 10 to the power 50 years or something to scan this space, which means that even with the best of AI, we cannot scan everything, right? So we cannot get the best material, optimum material faster. So what can we do? These are some of the techniques that we and others have developed in the field to tackle these challenges. And you can see that these challenges almost always occur in pairs. So the small and big data challenge is coupled with a big and huge data, huge design space challenge. So the most challenging scenario is small data and huge design space. When the available data is very small, but the space is huge. So we have very few to learn from, but the possibilities are huge. So some of these techniques, generative models and ML guided sampling, we just finished a project. There is a project on that, on this topic. These are the some things that we have been working on, and it's clear that we need advanced AI, machine learning, deep learning methods which are driven by HPC, and that's where I said like this combination of AI and HPC that we are interested in, that becomes very useful and important for these problems. So this is just a highlight summary slide of the works that we have in this space over the last 10 years. A lot of computer science publication, of course. I'm from computer science, but also we publish a lot in domain scientists, like domain journals, to expand our impact. Getting good readership, a lot of software tools, open source code available, patents, and so on. And you can see we have tried to address the small data challenge, the big data challenge, the big design space, huge design space, also some industry work, and so on. So of course, each of this is an hour-long talk, so I'll not go into details everything here, but I'll just give some examples of the works here to give you an idea, just 2 to 3 minutes each. This is one of our early works on LMNet, which was the first works of where deep learning was used to understand the chemistry of materials. So again, just let's take an example of Fe2O3. What is Fe2O3? Anyone knows its scientific name? Fe is ferric oxide. So FeO is ferrous oxide. Fe can have 2 valencies, +2 and +3. So Fe2O3 is the +3. So Fe2O3 is ferric oxide. So if you want to build a model or for predicting property of materials, we need to train it, right? We need training data. So let's say we have materials like this. We need to have some representation. That representation can come in different ways. One way is to just have, like simplest that you can think of is just the elemental fraction. Right, so let's say we have 100 columns, 1 column for each element, and each value just represents the fraction. So for Fe2O3, it will be like 40% iron and 60% oxygen. If you want to add some chemistry knowledge to it, we can have these kind of library of attributes, which we call physical attributes, where average atomic mass, average column on periodic table, average electronegativity, all these things can be used as a vector to represent it, and that way we're adding domain knowledge to the model. So that way NaCl and KCl, because they have the same valency, they will have similar vectors, not exactly same, but they'll be similar. So that way the model will know that if it's trained on NaCl, it will try to predict KCl reasonably well. So that's like adding composition information. Same thing we can do with structure. If we use something called Warner tessellation, we can quantify the environment of the atom and use that as a vector. So of course that is all very good, but as computer scientists, we were interested in the opposite thing. Like what if we do not give any domain knowledge? So we go back to the first representation, which is raw, just 40% iron and 60% oxygen, and it doesn't even know what is iron and oxygen. These are just 100 columns on the periodic table. It can be in any order as long as it's consistent. And then we found that using deep learning, as we increase the training data size, so you can see that this top curve here is random forest model using just elemental fractions. So just 40, 60 iron, this thing. And this green curve is random forest with these added attributes. So you can see the error goes down significantly. But this red or orange or brown curve, this is LMNet or deep learning using just the raw fractions. So same input as this one, but with deep learning. So you can see that for small data, it is worse, which is expected for deep learning. But as we increase data set size to about a few hundred data points, it beats this curve, and few thousand data points even beats this curve. So deep learning with only elemental fraction is defeating the random forest model with composition information, with physical attributes. And there are some more stringent tests like recovery of convex hulls, and also which I'll not go into detail here. So that was back in 2018 in scientific reports. And then a couple of years ago, we added an explainability layer to it, where we gave different groups of elements like combinations, and we found that group 1 and 7 combination is learned quite well, but group 3 and group 5 is not learned so well. So that helped us to like go back to the training set and see that why that's the case. And not surprisingly, the training that did not have enough representation in that space at that time. So when we add that, the performance can improve. But the point of this this exercise is that explainability is very important, especially for science and engineering applications where the cost of false positive is huge. If I get an email from Amazon that you bought this, you may be interested in this. Let's say I'm not interested. No big deal. I can delete the email. But if this says, oh, this is a new steel, very strong, you make your bridges from this, and now it's wrong. There's a big cost to that. So explainability of these models is much more important here than any other field. Of course, healthcare is the same issue. So that we know that the model is learning from the right features and not learning from the wrong features. So again, this is open source publication, Scientific Reports 2024. So this is when we have big data. But what if most cases we do not have big data in material science, especially experimental data is very small. In fact, we have one data set from NIMS Japan, which only has 400 data points, and it took them 50 years to get that, because each data point is a steel which they had to make and break to find out how strong it is. So that's very expensive, very time consuming, a lot of cycles and so on. So most of the time we'll have very small data. So how can we take advantage of deep learning there? So we take this idea of deep transfer learning, very common nowadays in form of pre-trained models. But we've been working with this for about 10 years now. So this is the work from 2019, actually, Nature Communications. So instead of making a model directly, let's say we have a small target data set, very small, that if we build a model directly from that, we call it the scratch model, training from scratch. But instead of that, we can build a model on a large source model, and then this source model, whatever it has learned, we can transfer the knowledge of this during the model training of the small target model. And this transfer of knowledge can be done in two ways. Fine tuning is one, which is the more common form of it, the pre-trained model that we use nowadays. And another way is feature extraction. So we can use this source model to extract features on this target model and then build a new model on top of it. Any machine learning, deep learning, and so on. So a few years ago, we did this in context of same property. So let's say simulation formation energy to experimental formation energy. Formation energy is a measure of stability. So lower the formation energy, more stable the material is. So for simulation, we have big data sets, hundreds of thousands of materials. But for experimental, it's hardly hundreds or thousands. So because it's difficult. So if we have a big data set of simulation formation energy, we can do this transfer learning, and that's what we did here. And we saw that there's a big drop in error. So even with less than 200 data points, this is model from scratch, and this is transfer learning model. We can have much more accurate model even with very small training data, and even with everything, we can have up to 50% better models. And but that was same property. What if we have different properties? Like we want to build model on these properties, but there is no similar properties available in the source set. What can we do? So the same property work was back in 2019 by Dipendra Jha, and then another student, Vishnu Gupta, a couple of years later, he extended it to cross property. So now we can build a source model on a different property and transfer it to a different property. And of course, there are limitations on where the transfer takes place successfully or not, which depends on structure awareness, and the properties which require structure are usually not transferable so easily, because this is all composition based. There is no structure used here, just raw elemental fractions. So, and we found that in almost all cases, out of 39 properties we tested, almost all cases transfer learning is better than a scratch model. And even when the scratch model is made more powerful with physical attributes, remember those average electronegativity, all those kind of periodic table information, if we add, the scratch model becomes more powerful, but still the transfer learning model using only elemental fractions can beat it more than half of the cases. And it is better extrapolated potential. So we all know that most of machine learning modeling, at least the predictive modeling side is curve fitting. So interpolation is not a very difficult thing, right? If we do interpolation well, that's great, but it's not very difficult. Extrapolation is where the challenge is, because you are looking out of the box, and materials discovery by definition is extrapolation. So here we did a very controlled experiment where the training was done on this part, and the evaluation was done on this part, because more negative means more stable. That's where we want to discover. So we see here that the scratch model failed miserably because it has not seen anything outside this, right? But transforming model is worse than this, of course, but is still much closer to the diagonal, right? These blue points. So this was very impressive to our collaborators from NIST. And this details are in the second paper of Digital Communication 2021. And then we followed it up with few more advances, like couple of years ago, we added a structure awareness to it. So as I said, previous work was only composition, just the elemental fractions and so on. But now we can also take advantage of structure, because we know structure is important, right? If you have learned from your high school, you may remember that graphite and diamond both are carbon, but the structure is very different, and that's why the properties are very different, the price is very different, and so on. So structure is important. So we are incorporating structure in this using graph neural networks, and we get similar kind of trends, that the scratch model is worse, the transformer model is much better, extrapolation wise also it's better. And here we tested on 115 different data sets, one of the largest that I've seen, and the transformer model was better in more than 100 cases. Again, open source publication, NPJ computational materials. And then following up with that, just last the LLM layer to it to make it more explainable. So now we have a GNN layer here, which is same as the last slide, but we also have now LLM branch, where we take a material, a postcard file, that's what it, in the format it's called, and then use something like a RoboCrystallographer to get a English representation, just a free text representation of this material, like this is this structure, this bond length, this so on, and then pass it through an LLM to get an LLM embedding. And so we have a GNN embedding and we have LLM embedding, and we combine them. So now this model is aware of both the structure and this LLM branch. Then we found that this concatenation or this combination or integration is better than having just this or just that. So we call it hybrid LLM GNN. And not only was it accurate, but it also gave us the ability to explain it. So here we see that between chemical information, structure information, and so on, the structure information is the most important. So the model is paying attention to structure information, which is kind of reassuring, because we want the model to learn that. Although we did not tell it to do that, but it is reassuring that it is automatically doing that. And even at the word level, we see that it is paying attention to these numbers. Again, we did not tell the model to pay attention to the number. It is just English text, but it is paying attention to these bond lengths and the technical names of the structures and so on, which is again important and reassuring that the model is doing the right thing. And this is again an open source article from Digital Discovery last year. This is one of our new collaboration that we started at Northwestern with Chad Merkin and Vinayak David, the pioneers in this field. How much time do I have? Almost, yeah. So I'll just, this is my, I think, second last exam. Yeah. So they have now the ability to do this kind of mega library thing, where on a very small chip, 2.5 centimeter by 2.5 centimeter, they can have millions of materials. So they wanted us to build some AI models to scan them quickly, because manually you cannot scan millions of materials. So we built a model for a quick quality check with high accuracy and low timing. And then we also made a segmentation model where you can, instead of getting data from each data point, we can now have this kind of acquisition boxes, which reduces the time and storage space. So both these are published in these, and there are a couple of patents pending on this work as well. And I think this is my last example. Toyota, as I said, approached us a few years ago. So we built some models for them for coercivity and remnants. And this is part of the work that I can share, because there's a lot that is behind the NDAs. But this is published work. So we built some models here with less than 5% error, which help them reduce a lot of waste and resources, and save resources, and then use it in the right direction. This is just from last month. I'm going to skip it, but in a one sentence, I'll just say that this is true inverse design using LLMs. So now we just give LLM, by fine tuning and all, these 4 different LLMs. We give it a prompt that here is a material with this property and this composition, and it will fill in the structure. So it's kind of magical, but it doesn't always work. But we tried with always like more than 100,000 different combinations, and we found at least 6 which were in the band gap of what we want for a semiconductor, and at least one of them had the right combination of phonon frequencies and so on. And I don't understand the full details here because I'm not a material scientist, but this is again just appeared online last month, so feel free to take a look. These are all the articles from computer science and domain from in this field. Also, a lot of open source tools and software available. I think I don't have time for a demo here, but please feel free to go to this website and you can use this tool to make predictions. And I just want to I'd like to end with this idea of false needles, wrong needles again. That it is, remember that AI stands for artificialness. So remember, people focus on the intelligence part, but I like to focus on the artificial part. Remember, it is artificial. And we as humans have natural intelligence, so we should not let AI take over. Either it's not just AI take; we are handing over the control. That is the bigger danger. So we should always remember that if you are an AI developer, then you should have very good fundamentals in AI and data science methodology, so that you can apply it. You don't make a model which is overfitting, or there are so many things that can go wrong while making model. And if you are an AI user, then we have to be careful that we use it wisely. We don't let it make us lazy, because I have seen published papers in good journals, which will start with a prompt. So that means that authors have not only used ChatGPT, but they have forgotten to remove the prompt. So they have become, we have become so lazy that we are not even checking. And same thing with students. I get submissions from students all the time. Students are addicted to ChatGPT. So my humble request always to all the students who want to get into this or already doing this is, don't become a slave of AI. No harm using it. It will save you 90% of the time. But 10% of the time, I do expect you to spend. Don't try to get rid of that 10% as well. At least go through that generated content thoroughly and make sure that you really want that to be submitted before you actually hit submit button. And you can see here there are big players here. Big companies have misapplied AI, not because of lack of expertise, because it is very easy to misapply. It seems very easy. You can take an online course, get some credentials, and call yourself a data scientist. But if you're not very careful, if you don't have the right expertise either in AI or in the domain, then we can fall into the trap of this wrong needles. So with that idea, I'd like to conclude and happy to take any questions. Thank you for your attention.
Hello, sir. Navdeep this side.
Yeah,
Like we were speaking about the novelty in research papers while using AI nowadays. So, how does explainable AI enhance transparency and trust in AI-driven scientific discoveries and research papers?
So in general, explainable AI will, there are different facets to it. So the explainable AI paper that I mentioned, this has some details on how it can be classified taxonomically. But in a simple way, it will tell you it will tell you where it is learning from. So I'll give you an example. There was a model some time back which was for wolf prediction. Like, cats and dogs models are there. There's a wolf prediction. Some of you may be aware of that. So it was very accurate to predict wolves. But when they did the experimental analysis, they found that it was paying attention not to the wolves in the image, but to the snow around it. So because there were snow wolves, so anytime there was snow in the image, it will predict as wolves. And it happened to be the case that the data was all with snow wolves, so it was getting very good accuracy. So that's why explainability will tell you where the model is paying attention, what features it is using, and what is not using. So at least it should not be using something that is known to be false. It may be it should use something that we know to be true. It may be using something else that we don't know. That will give us maybe new insights for new discoveries and so on. But here, for example, we definitely know that snow should not be the reason to classify an animal like snow would. So those kind of things will AI can help you determine. Like here, we know that why it is not performing well. Before this analysis, we didn't even know that group 3 and group 5 is not doing well. We just had an overall MAE number, and we thought that will be the error for all predictions. So hope that makes sense. Any other questions?
Good morning, sir. I am Aryan Raj. Sir, you talked a lot about LLM. I have just a simple question to you. Sir, what do advantage does LLM offer in automatic scientific literature review and the hypothesis generation?
So similar, LLM, basically it's like the machine will read many more papers than we can read, right? So that's the main advantage. If it understands what it's doing, and it is able to give output in a way that is comprehensible and that has really insights, that is the main advantage of LLM. So that's what we did here. By converting a structure to English text, it could extract more information out of it. But hypothesis generation is a completely different. In fact, many people don't know this, but hypothesis generation is not something that happens every day. In a whole sentence, it can happen one or two times. So the real, out of the box hypothesis generation, look, it's not something that you can drive so easily. So there is some promise with its LLMs and all that it can comprehend all the available information much more faster than a human can do. So maybe it can give us the right direction. But it's like materials discovery. We have millions, or not a million, 10 to the power 100 combinations plus, and we may have 1,000 million or something observations. Now, AI may give us directions to look at, but it will not immediately tell us, oh, this is the magic material. But that is enough. Instead of searching all possible scenarios, if AI can direct us that, okay, this is promising, then we can focus our power there. So that is a similar thing that can happen with the LLMs in terms of possible hypothesis generation. But I'll be surprised if something like that happens very soon. But it has potential. If not, feel free to reach out later. My information is all online. So thank you so much. Right.
Thank you so much, sir, for your insightful words. Now we invite Dr. Keech Ringam, a PMO specialist with over 15 years of experience in business consulting at the executive and senior leadership levels. Throughout his career, Dr. Shringam has provided valuable expertise in areas such as business strategy and planning, the application of ICT in business, program management and turnaround, business resilience, and change management. He is recognized as a thought leader and a skilled speaker, particularly in the realm of business application of information and communication technology. Mr. Keith's contribution extend beyond the consulting world, as he has served as a board director of Australian and Computer Society and a guest lecturer at various universities, sharing his insights and practical knowledge with future generations of business leaders. He has joined us today to talk about project within the AI business regime. The stage is yours, sir. Over to you, please.
Good morning, everyone. Can you see me and hear me all okay?
Yes, sir, you're audible and also visible.
Beautiful. I'm here in sunny Sydney. I'd love to say that that's the view out of my office, but that's not quite true. So what we want to do today, as you know, this session's being recorded. I'll share the slides afterwards. If you have any questions as we go through, just raise your hand and we'll allow time at the end. Madam Chair, if you can keep me to schedule, that would be much appreciated. My profile's been gone through. Now, the one bit I'm going to say is, if we're using terms that you're unfamiliar with, by all means Google them, use AI throughout the session. If you come up with something from AI, all we need to do is know where you used it and the errors that you found in using it. So we're going to do a quick introduction. We're going to look at demands from projects within business application of AI. Look at some aspects of a project management regime around AI, and wrap up with questions and comments at the end. So let me just go through a few points, then I want to pause and let everything soak in. Business needs different AI types to work together. You need robotics, integrated with IVR and chatbots. You need imaging and facial recognition integrated with generative AI. And this needs to be done across your vendors, your business partners, your systems, and the data. We won't get into the AI race today but as a separate topic. But very quickly, there's two broad approaches. There's one size of AI fits all types. So the AI to grow lettuce is going to be the same as the AI to control fighter jets, which is going to be the same as the AI used in managing projects. The market may say that that approach is right. If you look at a lot of other players, and if you look at China, they're going down the path of sovereignty of models, data, and integration of AI types like we just mentioned. They're going down the path of business-specific integrated AI, smaller models, specialist data, tailored to specific needs. The focus in other countries is embedding AI in chips, devices, and applications. And we know that the Indian Minister for Technology has outlined similar challenges and opportunities for India. The reason I mention that is this. Currently within project management, there isn't one size fits all AI for project management. AI is driving the demand for projects much more than AI is transforming projects. That'll probably change in the future, but this is the current situation. A couple of bits to go through. If we consider AI as a user of data with roles, responsibilities, and accountabilities and liabilities, we're in a much better position to manage it within projects. I know there's legal issues, but it's a principle. We all know the importance of data. We all know that the take-up is varying with budgets, resources, that sort of thing. We all know that sovereignty of data centers, data, models, and AI integration is becoming a big topic. One of the ones that's impacting projects is definitely cyber security. Now, we're covering a lot of ground quickly, but we will share the slides and you can go through them at your leisure. So before we move on, any quick comments from the conversation we've had to date? Madam Chairman, has anybody raised their hand in the room, and can anybody see any questions online? Sorry, was that a comment? I couldn't make it out.
So we will ask the questions at the end. You can continue.
Yep, not a problem. Thank you, everybody. So what I want to talk about is AI is driving demands for projects. Right. Park AI for a minute. The core fundamentals around projects, managing scope, governance, risk issues, they're all the same. AI isn't changing those. AI is just a tool at the moment which is used for the automation of the routine. The people, the processes, the data, the technology, and the governance and the human factor that it takes to deliver projects remains important. Now, AI is increasing the demand for projects to transform the business. It's driving a greater skill set and expertise. It's requiring more people have project expertise. More projects require more resources. It's driving the embedding of data and technology, and it's driving the automation for running the business. Now, very quickly, within a business, you've got two areas. Run the business, which is the routine operations that keep everything going and pay all the bills, and you've got change the business, which is how we improve the business, and that's mainly project driven. Now, we have roles of research, design, develop, test, operations and services, consuming, managing, and assuring. All of these apply to both run the business and change the business, and AI is driving the skill sets within all of these. So as project managers, this is the challenge that you'll be working with. Now, the performance of projects is driven by people, politics, processes, the price, how the project is positioned, how the project is packaged up and getting everybody's buy-in and support, and the presence that the project has within the business. And it doesn't matter whether you're doing a construction site, you're running the latest AI-driven projects. These skills are becoming more and more of a premium as more AI is used. So, to deliver a project, we have to manage people. We have to manage finance. We need to manage vendors. We need to manage change and those sorts of things. So project management is not just Prince2, PMBOK, and project management frameworks. It's all of these other frameworks that are needed. And these skills are needed across the projects and across the business, and AI is driving this. Now, don't worry about this one being a little bit complicated. There's a very simple message. Projects work across all these business areas and require people from all of these business areas. The human factor is going to be of increasing importance in project delivery the more we use AI. So let me just move on a bit. Okay, do we want to pause there and do any questions, or just leave the questions to the end?
So we can do the questions at the end.
Okay, I'll keep going. Thank you, everyone. Now, projects are delivered through an emergent behavior. You change the environment in which the people are working. If their interests and values are aligned, they'll work on the project. If they can realize benefits and outcomes that meets their needs, they'll get involved on the project. Doing a project, you need to take the people on the journey. Yes, there's leadership, strategy, and decisions, and we need process and information. Now, you see this every day of the week, whether we're building a new metro system, whether we're building a road, or you're doing your assignments for uni. These remain important, and AI is driving the emergent behavior approach. Now, within projects, it doesn't matter whether you're doing an advertising project to sell sand shoes or you're running a zoo to show off Indian elephants. Cybersecurity is being intensified with AI. There's more attacks that are occurring faster, greater exposure, and those sorts of things. These require a whole of business response. So when you're managing projects, AI is going to intensify the needs for cyber security within your projects. Now, you can learn everything you want to know about project management on your phone. You can learn the entire Prince2, PMBOK, whatever it is. What it does not give you is the professional skills, which we've talked about before, the ability to manage stakeholders, the industry practices, the industry contacts. And as we talked about, getting people to work together to deliver projects through an emergent behavior is key. So if anybody is bored doing project management and thinks they can learn it all on their iPhone and not attend lectures. I would love you to prove me wrong, because I'm going to say to you, yes, you can learn all the theory, but if you're not in the room collaborating together with your stakeholders, you're not going to get your projects delivered. And AI is driving the need for this. Okay, a couple of other bits that AI is doing. AI is going to help with managing the complexities and interdependencies of projects. What it's not going to do is to make sure that things are approved and authorized. So if we change the number of cement trucks turning up to a construction site on Wednesday because AI has changed the schedule, if we haven't made sure that all the stakeholders know that and all of the workers are turned up accordingly, then you're just going to have a fleet of cement trucks that are full waiting for work to do. Now, one of the biggest take-up areas of AI is in the routine reporting, notification, and monitoring. And as we've just mentioned, making sure that the changes are seen, making sure that we manage exceptions and expectations and those sorts of things. That's where more and more skills of project management are going to come in, and more of the time is going to get consumed, and the need for the human factor. Now, we're going to use various models within project management. If we don't have a proper lessons learned database, if we don't have previous project documents, if we haven't flagged the identifiers in previous projects, if we haven't managed the change request, if we haven't managed the contract agreements properly, and we're training our models, if we're missing this, the models are not going to give us the project management that we need. What it's going to do is increase the human oversight and effort required, not reduce it. So if anybody thinks that they can just take an LLM off the shelf and run a project from it, please consider this aspect. Now, one of the biggest issues within project management is putting the controls in place to make sure that everything gets delivered. If you're unfamiliar with the term controls, look it up. Controls are how you assure the quality and delivery from projects. The human beings involved need to know what the controls are. They need to know how the controls have changed. They need to know how the controls are going to impact their contributions to a project. So again, AI is going to help with the development and application of controls and help with the monitoring and that sort of thing. But we need to make sure that people are adopting and are using the controls. Very quickly, yes, we're going to use AI within schedules, tracking, and those sort of things. And again, the human aspect, the review, the agreement, and managing of the changes becomes the premium, and the project manager's role becomes more focused on that. And this occurs across projects, programs, portfolios, and project management offices. We've labored the human factor again. Those who I had the privilege working with in January when we did a workshop, here's an example of the workshop approach that we did in Malaysia, and this got the buy-in and support. So please consider that. Now, we're running out of time, so I want to just do a few more slides. AI requires the strengthening of a three-line model. To assure the delivery of projects, you use a three-line model. Some level of audit, some level of governance with support and shared services, and the front end owns the issues and owns the delivery. With AI, you need to make sure that this three-line model is coming through. And the previous speaker has already mentioned some of the challenges around AI. Now, one of the big ones is the business prerequisites need to be there. If in a business you have no understanding of cybersecurity, how are you ever going to address cybersecurity? The more we use AI, the more projects we run, the more complicated the projects become, the greater the dependency is upon business prerequisites being there. So I just want to wrap up. What are some of the things that we can do and take away? We can have project management expertise in dedicated content within schools, TAFEs, unis, private colleges, and that sort of thing. We can do awareness of frameworks, processes, and key documents for projects within business procedures and knowledge of these business procedures within projects. We can ramp up the professional skills as we've talked about, the use of scenario activities to drive outcomes and experience. So I'll give you a couple of examples. In your course, not only should you be learning about controls, not only should you be learning about the use of AI generated controls, but we should be learning about how they match practical industry delivery and the effectiveness of the controls. We've talked about having training data for the LLMs. So if we're using AI to help us write schedules, we need to understand our training data. One of the ones is we need to be able to review contracts to make sure that vendors are delivering the right things so that these get into the future project plans. And of course, we need to skill people up and address HR. In the slide deck, there's some links, which I'm not going to go through now in any detail. And let me pause there. Okay, Madam Chairman, back to you and over for questions and comments. And everybody, thank you for your time. I'd love to hear your questions and comments.
Okay, now the floor is open for questions. Any questions?
Business models measure performance and impact of AI deployments.
Sorry, can you say that question again, please? I missed it.
How do business measure performance and impact of AI deployments?
Right. Let me relay the question to you. How does business manage the impacts and performance of AI? Is that your question?
Yes.
Okay, there isn't one single measure. There isn't one single approach because it's going to vary with your business, the areas within the business, the markets that you're in, the industry sectors that you're in, the business types. The performance metrics on a construction project are different to the performance metrics for remediation for anti-money laundering within a bank. What we know and what we have to measure is this. We need to know why the project's been set up, what we're delivering, what is the cost, what is the expected benefits and return, and we can use AI to help in defining those, tracking those, reporting those, and in managing the outcomes. Sir, does that answer your question?
Hello, we have one more question. Hello, sir. My question is, how can businesses ensure scalability and sustainability of AI solutions?
Okay, how can businesses assure the sustainability and scalability of AI solutions? First of all, there has to be executive buy-in and support. There has to be budget. There has to be resources allocated. The resources need to have the required skills and expertise and spend time away from business operations to spend time on the activities. Businesses, again, have a series of measures that they use to achieve these things. Now, two other aspects. If we have an underperforming business process, AI is not going to fix it. AI is just going to highlight the gaps and increase the proliferation of errors. One of the biggest factors in the take up of AI is the quality of data, the use, application, and availability of data. So we need to address that as well. One last bit. In a larger organizations, we have various controls in audit and assurance and those sort of things, especially in highly regulated regimes like aviation, banking, and those sort of things. The audit processes still need to audit the business outcomes, but they need to know where AI is used in the business processes so that when problems turn up, they can push back through the audit process in the usual way and address the issues coming out of AI. This is a much longer conversation that I'd love to take offline with you, but does that answer your question for now?
Yes, sir. Thank you so much, sir, for your insightful words.
Good. Okay. Are there any other questions or comments now? Because we've been going for about 30 minutes and we've covered a lot of ground. So please.
No, sir, no questions. Thank you so much.
Okay, can you please share the slides and the recording with everybody afterwards? And everybody, thank you for your time and your attention. Sorry I didn't make it to Delhi, but I was there in January for Confluence. So everybody, thank you very much and have a great weekend.
Thank you, sir. It is my pleasure to invite Dr. Vishnu S. Pendelia, Professor of Applied Data Science and Academic Senator at San Jose State University, USA. He also serves as Chair of the IEEE Computational Intelligence Society, Santa Clara Valley Chapter, and as Distinguished Contributor of the IEEE Computer Society. He is the author of the book Veracity of Big Data. He has contributed internationally through programs sponsored by the Government of India and has served on proposal review panels for the US International Science Foundation and Canada's NSERC. We are truly honored to have him with us today. He has joined us today to talk about AI through its inflection point. May I now request Sir to take over, please?
Yes, thanks for that kind introduction and thanks for the invite. Is everyone able to hear me and see my screen?
Yes.
The slides?
Yes, sir.
Okay, thanks for the confirmation. So I came up with this topic before I knew the duration. So, so it's a long topic, but I'll try to keep it short in the time given to me. So AI through its inflection points. So we are not merely observing a technical evolution, but a fundamental shift in how intelligence is conceptualized, engineered, and deployed at scale. So today I don't want to talk about incremental progress, but about inflection points, moments where the curve bends. So this is where yesterday's assumptions stop working. AI, we all know, hasn't grown linearly. It has leaped. Each leap changed not just technology, but power, economics, and society. So this is the story of those bends in the curve. Okay, so an inflection point is not like version 2.0. It is not a faster chip or a better benchmark score. It's when the rules of the game change. It's when the entire industries reorganize. It's when research funding flows in new directions. It's when yesterday's leaders disappear. AI's history is a sequence of these structural shifts that we will cover in the next few minutes. So, reconfiguration of economic value, shift in research priorities, new power structures. So, that's the kind of thing we are trying to talk about. So, the keynote roadmap follows the chronological history, sort of. So, we began with logic, then we shifted to statistics, then deep learning, and the deep learning that reshaped perception. Then the foundation models, which unified everything. And now we are entering embodiment. So this is not just technical evolution, it is a redefinition of intelligence itself. So the talk will follow this path. So early AI believed intelligence was symbolic manipulation. The mind was seen as a logical machine. So if you could write the rules of the world, machines could reason about it. Intelligence was primarily based on deduction. It was elegant, it was clean, and it was mathematical. And completely dependent on us describing everything. So experts sat down and wrote rules. So if X, then Y. Thousands, millions of such rules. No learning occurred. The system only knew what we told it. This was the good old fashioned AI. It was powerful but fragile. So my undergrad senior project was in this direction. I used Prolog. Prolog is a language. It's a declarative logic programming language. It works by defining a database of facts and rules, and the engine automatically infers solutions using backtracking and unification. So unification is the fundamental mechanism in Prolog for matching terms and assigning values to variables. So using these constructs, I created a question paper setting system. It's a prototype knowledge-based system. So the rule base ensures balance across topics, cognitive levels, and question types. And the inference engine selects questions that satisfy exam constraints. So obviously there is a motivation for this. So it was quite acknowledged in multiple circles. But the peak of this paradigm was in 1997. So it's like the AI's high water mark. So Deep Blue defeated the world chess champion, the machine defeating a human chess champion. So, but it wasn't thinking like a human. It was searching massive trees of possibilities. So brute force guided by heuristics. It mastered a closed world. And that distinction, the closed world, is critical. So it proved machines could master complex closed system logical games. But chess rules don't help you drive a car. Rules don't generalize easily. The real world has infinite edge cases. We hit the knowledge bottleneck. So we cannot hand code reality. So the Polanyi's paradox on the slide, we know more than we can tell, haunted us. So we know more than we can explain. Symbolic AI was powerful, but it was brittle. So we stopped programming rules. We started programming with data. Instead of here's the logic, we said here are the examples. Certainty gave way to probability. Intelligence became inference. This was the conceptual earthquake. So that's the era we are still continuing to be in as a foundation. So in this paper, authored, the two co-authors are high school students at the time the paper was, the work was done. So what we did was, our goal was to research if machines can learn subtle musical properties like the music tonic. So tonic is like the G major and things like that, right? So we wanted to find out if machine learning can detect the tonic directly from audio instead of us hand coding signal processing rules. So we do not feed waveforms into a giant neural network and let it discover everything from scratch. We deliberately pick signal representations like MFCCs, bark frequency features, MEL spectrograms as inputs. So a human expert is still the one who decides these are the aspects of the audio that the computer should look at. So the takeaway from the work that we did was that with enough examples, statistical models learn internal musical rules well enough to automatically detect fine-grained details that musicians usually infer by ear. So, but the problem was humans still design the features. For instance, in vision, uh, uh, features like edges, corners, color histograms had to be designed. In language, n-grams, bag of words, and features like those had to be designed. So we told the model what mattered. So performance plateaued. Models were only as smart as those features. So the bottleneck shifted, but it still remained. So we still had a bottleneck. So then came hierarchical representation learning. So this is the era when neural networks began learning features themselves. So AlexNet shattered benchmarks overnight. Error rates dropped dramatically. The community was stunned. This wasn't incremental progress. This was an inflection point. Scale plus GPUs plus data unblocked performance. Perception became solvable at scale. So for the first time, machines rivaled humans at object recognition. So this is a convolutional neural network framework. So vision moved from brittle pipelines to end-to-end learning. The world became machine readable. Surveillance, medical imaging, autonomous vehicles, everything got accelerated. And perception became infrastructure. So the way CNN works is the lower layers in the neural network see edges, the middle layers see shapes, upper layers see objects, and the machine was discovering abstractions through this process. So that changed everything. So we used a type of CNN called the efficient net to, of course, in conjunction with a probabilistic data structure called the Bloom filter to speed up pandemic detection. Right? Because in the pandemic, when a pandemic happens, hopefully it doesn't happen again in our lifetimes. If it strikes again, every minute in advanced detection results in thousands of lives saved. So the work we did creates a fast pipeline. So the high risk profile signatures that are inserted into the Bloom filter help us determine very quickly whether a new patient is impacted by pandemic. And but the problem with Bloom filter is it's a probabilistic data structure, right? So Bloom filters do not produce false negatives, but they do produce false positives. So false negatives are outright ruled out. I mean, false negatives, if the case is false negative, or if the case is negative, that means the patient is determined not to have pandemic, then we are sure that the patient does not have pandemic. But if the Bloom filter says the patient has pandemic, then we need to process further because it could be a false positive. So that's when the efficient net CNN comes into picture, and we take the x-rays and we do all that stuff to determine whether the patient has the virus or the pandemic, right? So that's a fast and efficient way of determining whether a person is suffering from pandemic. So we published it in a journal very recently. Then came, or in parallel came the reinforcement learning paradigm in a big way. So in 2016, AlphaGo combined deep learning with search. It didn't just calculate, it evaluated. So there was a move, number 37, that shocked the world. Many human beings thought that it is wrong, that move, but it optimized long-term probability. It demonstrated machine intuition. So that was psychologically transformative. So, so we are currently working on some exciting ways to use reinforcement learning to solve problems, but the work is still under review by a couple of reputed journals, so I didn't want to use that work for this presentation, but hopefully it will be up in my Google Scholar pretty soon. So the whole paradigm shifted from rule basis to data as the oil. So the word moat refers to a unique competitive advantage that protects a company's profits and market share from rivals, right? So, so we generate staggering amounts of data daily. Code became open source, data became the competitive advantage, and the moat shifted from algorithms to data sets. Data became oil, economic power consolidated around data ownership. So that's how Google derives its power. The predominant power is from the data that it owns or that it has access to. So then came the foundation models, the transformer architecture, the large language models, and of course the unreasonable scale. So before the transformer architecture, researchers and machine learning engineers used to use what are called as recurrent neural networks. They were really sequential and pretty slow. Then they started using RNNs with CNNs to make things faster. But transformer changed it all. So transformer changed the architecture. So everything is being processed in parallel now in the transformer architecture. Attention lets models weigh relationships dynamically. Context became fluid. So this was architectural elegance meeting scale. So performance scale predictably with compute. So larger models kept getting better, and there was no obvious ceiling. So the more parameters, the better the models were getting. Intelligence became a function of scale. So this was unprecedented in AI history. Then the generative capabilities led to a whole gamut of applications. AI moved from classification to creation, from answering to generating. Text, code, art, music. The cost of content creation almost dropped drastically. Creativity became augmented, and this democratized production. And of course, it disrupted industries. So generative AI has also led to surge of highly realistic fake images online. So this amplified the misinformation risks. So there were detectors, but the traditional detectors of fake images struggled to keep up with new generation methods, and they also lacked human understandable explanation. So that's when we did this work. We used the large multimodal foundation models, the vision language models, as feature extractors for fake image detection. Then we integrated explainable AI techniques to highlight image regions or cues that drive the fake real decision, improving transparency. So this work demonstrated that multimodal foundation models can improve fake image detection performance over conventional baselines. So essentially, the foundation models and the generative AI, the boundaries between modalities dissolved. Text talks to images, audio becomes text, video becomes searchable, models now see, listen, and speak. Intelligence is becoming unified. So then the next era is embodied AI. It is often said that body is not a vessel of the mind or vessel for the mind. It is part of the mind. So in our spiritual philosophy, they say that soul is encompasses the body, right? So just like that, mind and intelligence encompasses the body. Intelligence comes through body and interaction with the environment, right? When the environment is stressful, we are not intelligent, right? Our brain stops thinking, obviously. So embodiment plays a very big role in intelligence. So that is the next movement. So large language models are brilliant but disembodied. They are brains in a jar. They are working somewhere in the cloud, and they are kind of dissociated with the real-time environment. So they predict words, but they don't predict physical states. True intelligence requires interaction. It is more dynamic in nature. So understanding comes from doing. We all can relate to that, right? That's the whole purpose of homework exercise in the schools. So we are now combining language models or the large models, foundation models with robots, from scripted automation to instruction following agents. So we say pick up the blue apple, and the robot picks up. So this is not too new because with the foundation models, we were able to tell the model to do the same, right? We could say, create the video of a robot picking the blue apple, and it would create a video of the robot picking a blue apple. The same thing that was in the video context, and now it is in the physical context. That's the only difference, right? So it is it's a shift to embodiment. So intelligence now has a body. The robot is the body. So language meets physics. So this is a profound shift. So real world operation requires causality, not just next token prediction. So next state prediction, we need next state prediction. So we need internal simulations of physics. AI must learn how the world evolves, right? The main difference between asking it to create a video and asking it to program a robot is the physics, right? In videos, there's no physics as such. But with robots, you need to take care of the physics and the real world environment. So AI must must interact dynamically with the environment. So that is the frontier. So we are going to offer a course in embodied AI pretty soon. So currently my students are working on some homework assignments. So typically I make sure that the homeworks are tested by student assistants first before rolling them out to the students in the class. So that's what is happening currently. The students are testing out homework assignments. So this is one of the assignments, to use Isaac Sim to pick and place a block. So that's what this robotic arm is doing, right? And you can see the log messages coming in through. So that is where we are currently. And of course, we are also trying out some research problems. It is still it's still at a very beginning stage, the research part of it, but students are working on that. And what else? Yeah, the future. The talk cannot end without talking about the future inflection points, right? So we had chatbots to answer questions. We had co-pilots to assess tasks. And now in the future is all about agents. Agents pursue goals. So the locus of control gets shifted. Planning and execution become autonomous. So this will define the workflows. But autonomy introduces risk. So who defines the goals? How do we encode values? And ensuring alignment with our human values is a challenge. So technical alignment is hard, political governance is harder, and this is not optional, it is urgent. So I made this call a few months back, or maybe. So there's a lot of call for regulating AI. Some of the senior folks in the industry. So there is a lot of discussion about this. You can watch it online if you're interested. In fact, I gave multiple talks on these topics. But the future is not about AI versus humans. It is humans plus AI. Only then we can say that AI is successful. So that brings us to the centaur model, right? Like in chess, the human-machine partnership. That's a concept introduced by Gary Kasparov in 1990s. I think it was called advanced chess at that time. So the idea is AI amplifies cognition and humans provide judgment. The humans act as a meta-strategist, deciding when to trust the AI, when to override it, and selecting which analytical style to use. So this is like an exoskeleton of the mind. So we know exoskeletons are wearable, rigid, or soft mechanical frames that enhance human strength. So this is like this concept is like the exoskeleton for the mind. So in summary, symbolic AI was logical but brittle. Statistical AI was probabilistic but shallow. Deep learning scaled representation. Foundation models generalized across domains. Embodied AI grounds intelligence in physics. And the future is autonomous and collaborative. Each inflection redefines intelligence. So with that, I'm opening the floor for any questions. So we are indeed living inside an inflection point. not just watching it, we are living it. So the question is not whether AI will change the world, it already is. The question is how will we shape it? So with those few words, I will be happy to answer any questions.
Sir, actually, we are running short of time, so the students can mail you the questions they have.
Yeah, sure. I put my contacts on the slide so they can connect with me and then email the questions.
Okay, sir. Thank you so much, sir, for your gracious words. It's now my great honor to invite Professor Sardar M.N. Islam from Victoria University, Melbourne, Australia. Professor Islam is a distinguished academic with an outstanding record of research excellence, international recognition, and keynote engagement at major global conferences. He served on the editorial board of 14 reputed journals and has successfully secured several large scale research grants. His work span advanced computational mathematical models, computer science, quantum computing, artificial intelligence, data science, and analytics. An international respected researcher, Professor Islam has made significant contributions to AI, quantum technologies, game theory, business, and analytics, and advancing mathematics. With application across engineering, healthcare, and industry, we are truly privileged to have him with us today. He has joined us today to talk about research advances in computational engineering and computer aided engineering in emerging technologies and application. The stage is yours, sir. Over to you.
Thank you.
Excuse me, sir.
Ladies and gentlemen.
So we are short of time, so can you please be quick with your presentation?
Yes.
Okay, sir.
Okay, so can you see my slides?
Yes, sir. Your slides are visible.
Okay, that's good. Okay, ladies and gentlemen, that's the topic of my presentation. I will try to make it short and maybe leave for a few minutes for questions and answers. So the topic, as you can see, is the recent advances in computational engineering or computer-aided engineering. I know this is the IT conference, but bringing engineering is a bit outside the main focus of the conference. However, I'll try to focus on the IT aspects, computer science aspect of the topic, and make it more or less engineering focused. So, as I said, given that time, there will be not enough time to go through all the issues. So, if you have any question, comments, and if you want to follow up anything, you can send me an email. My email address is there, or you can connect me through LinkedIn. So, the topic that I will actually discuss very briefly, this the digital engineering, in engineering, sometimes we call digital engineering, we can say computational engineering, or engineering informatics, computer-aided engineering. So these are different concepts. So what are their foundations? That I will discuss briefly. Then the role of artificial intelligence and machine learning in engineering, and then some of the other recent developments like AI agents, multi-agent systems in engineering, and quantum AI agent, hybrid quantum classical frameworks, agentic programming, and autonomous software systems. These are and also digital twin and cyber physical system, which is a very important topic in digital engineering or IT applications in engineering, and then of course some advanced topics in engineering like computational fluid dynamics and so on. And there are some also some developments in mathematical foundation of all those technologies like more recent optimization methods, game theory and chaos theory are also being applied. So I will discuss briefly that, and also an important area of recent developments in digital engineering is the application of quantum computing and quantum technologies for engineering systems. The issues of smart manufacturing and Industry 4.0 or Industry 5.0, and the application possibilities for application in not collectively in digital engineering, but also different areas of different disciplines of engineering, civil engineering, infrastructure, energy, biomedical, robotics, electrical, mechanical, and so on. And what is direction the future AI-driven engineering system is going, that I will just have some comments. So the digital engineering or computational engineering, this is they just introduces the application of computers and IT in different areas of engineering, different disciplines. That is broadly we call say digital engineering or computational engineering. Is traditionally maybe 50, 60 years ago, all the engineering research were being mainly done in the real physical laboratories without really application of many computer programs or computer simulation, that physical experiments and physical development. But this real physical experiments and research in engineering is has several disadvantages because they are costly, time consuming. There are safety issues and other limitation of the hardware physical systems. Therefore, they increasingly the engineer they have started using computer systems to do their research, and instead of really using the real life physical system or engineering system, this a real physical engineering system now can be simulated on the computer, and the research can be done on the computer using this computer simulated system. And how does it operate? We can get more insight from there, and also how to improve the system. We get that information from the computer simulation. And so this become cheaper, just within, also easier, convenient, and sometimes even can give more accurate information about engineering, research, development, application, and deployment. So this area is called digital engineering or computational engineering or engineering informatics, or sometimes we call computer aided engineering. So we can see in this area the engineering systems are designed, analyzed, and improved not through in real physical laboratory, but on the computer, on computers. and then the result then can be applied to real life application. So that is digital engineering or engineering informatics or computational engineering. So what are the advances in this area? So to understand the advances, we have to understand what are the recent advances in computer science and information technology, IT, or what are the recent advances, because these recent advances in IT and computer science have been applied to the digital engineering or computational engineering, and then these developments in computer science and IT have also affected or advanced the computational engineering. So some of the recent developments in computer science and the computer science and IT are the following, and these are also my areas of interest and expertise. So the one area of recent development is artificial intelligence agents, and then we can also do quantum artificial intelligence agents, and also more serious developments in the embedded systems, because especially in engineering, many of the engineering system, we have to do embedded systems, because we do programming to include in the physical engineering system. So there have been changes, developments in embedded systems and also embedded programming. And also there is another area of development in computer science and IT is the AI assisted programming, artificial intelligence assisted programming. Like in the past, if we are developing programming and software engineering, we may have to spend several years to develop a good software and program for large scale applications. But now this coding and programming, even deployment and debugging, all these tasks can be performed by can be done by artificial intelligence. So the developing a software that might have taken 2 years or so now can be developed within a couple of days. So that is another area. So collectively we can say agentic programming or AI assisted programming or autonomous software system, and also quantum computing. This is the most important development in computer science, but not only in computer science, but also in the whole world. Based on the quantum physics, now we are using quantum computing, and the quantum computing is a fundamental development in the current world. And this quantum computing and quantum physics, quantum technologies have substantial implication or application to digital engineering. And another area of development in IT or computer science or even is digital twins. Digital twin or cyber physical systems. This is in the borderline between computer science and engineering and physics. So in digital twin, what is done, like for example, if we think an engineering system, like for example, a water distribution system, engineering system, and then we have the real physical engineering system, but on the computer we can simulate the system exactly the way it developed, it is developed and operates on the on the computer, and then so it's actually the computer simulated system is representing the real life physical system, for example in the water distribution system. So and then we can use this computer system to exactly monitor how this the for example water distribution system is performing. Is there any problem there? Is there any leakage there? Do we need to take any action there? So this this sort of monitoring or management, we don't need to go to the water distribution system in the field, but we can do it through computer. So with a digital twin, that means is both this digital system representing the computer simulated system, but also the physical system. So this is an important area for digital engineering or computational engineering, and there have been more extensive application of this computing system to this type of engineering areas. And also there are because we are talking computational engineering and also digital. So computational means sometime in computational system we have to use mathematics, or at least we have to understand, when we are doing all the above technologies like AI agent, embedded programming, quantum computing, and digital twin, there are mathematical techniques, methods, which are being there are mathematical foundation of those technologies. Sometimes we don't know the mathematical foundation, we can simply just do the coding and make the app. But if for advanced research, we need some time to understand the mathematics behind it, and to develop and improve better system. But sometimes these systems can be also, the technology can be more mathematically focused. So some of these mathematics which are being used extensively currently in digital engineering are optimization methods like operation research methods in game theory and chaos theory. These areas also have some special applications. There are other mathematical methods, but I have included these three areas of mathematics because these are the areas of my interest and expertise. I have many publications and supervision experience in that area, so I'm very familiar with the literature in this area. So this, I have just discussed the general overview of the concept of the digital engineering, and we have seen that digital engineering means essentially application of computers and also IT to develop studies, simulate, apply, and deploy engineering system. And because in the presentation, my current presentation is just focusing on the recent advances, not the previous methods or the old methods. So therefore, we are talking what are the changes have occurred in these areas in recent years. And so to these changes in these areas have come from the developments, recent developments in IT and computer science. So I have discussed what are the current the recent advances in computer science and IT. So that gave us, the background of this presentation. So what are the changes, the recent advances in IT, and what are the recent changes in, computer science? These changes have been impacted and made the recent changes in computational engineering also. So the similar area, like the recent developments in computational engineering will be, the application of AI agent and quantum AI agent in engineering, application of embedded system and embedded programming in computational engineering, application of agentic programming and autonomous software systems in digital engineering, application of quantum computing in engineering. That is another area of recent development in digital engineering. The application of digital twin and cyber physical system in engineering. This is another area of the recent development in computational engineering. And also some of the recent, these technologies, some of the recent the applications of mathematics or mathematical foundation, especially from the area of optimization, game theory, and chaos theory. This is also another area of the recent development in computational engineering. So essentially, as I said, we have seen what is digital engineering and what are the changes in the key advances in IT and computing systems. So these recent advances in computing IT, these are the areas of recent advances in digital engineering or computational engineering as well. So the rest of the presentation, I have discussed and elaborated this in detail, but for the time constraint, and as you know, now we don't need to go into detail of this in a short period of time, but essentially I'll just go through the slides. Like this is the area of application of AI, artificial intelligence engineering. You know that we know that many of the systems in engineering, there are extensive application of artificial intelligence, and AI agent is the recent development in artificial intelligence. People say that this is the most transformative technology in 2025, AI agent. And AI agents also are being or can be applied extensively in digital engineering. And of course, when you apply AI agent, we can make another version of AI agent based on quantum computing. And as I said, another area of development in computer science is the AI assisted programming. So this instead of manual coding in computational engineering, we can use AI assisted programming methods that makes the computational engineering research and development extremely convenient and easy. And of course, with many of the development in engineering are also coming from the embedded systems and embedded programming, of course, and digital twins and the cyber physical systems have extensive and the potential of extensive application in many different real life areas in engineering, in all engineering systems. And of course, simulation and computational modeling we can do using the recent advantages in quantum, recent advantages computing and IT, more core engineering, simulation, and computational and modeling area. We can use, very recent developments in optimization methods to develop more engineering system. And game theory has also traditionally been used also in engineering system extensively, many different engineering areas, especially when we want to develop cooperative or more integrated systems where different AI agents or different technology need to collaborate, cooperate, and develop an improved system in those sort of situation. The game theory can be also used very usefully. There are almost all engineering areas it can be used, but especially energy and transport. And of course, this complex chaos theory and complex system in engineering, because all engineering systems are very complex, and the real life many things we see they can be classified as complex system. For example, the weather system, meteorology, then these are also complex system. And to do simulation and application and analysis, we can use chaos theory in those areas. And as I said, the most important and useful and significant development in digital engineering or computational engineering is the possibility or ability to apply quantum computing or other quantum technologies for developing, simulating, managing, and designing engineering systems. So this is probably the most important area and which has the most future prospect. We can have a hybrid because many people may not be still familiar with using quantum technologies and quantum computing, and the quantum hardware has still some limitation. Given then we can also use just the the hybrid system in quantum computing is possible to use both quantum and classical computing system together to apply generally the quantum principles. And there are many applications of computational engineering, even for example in digital, in civil and infrastructure engineering, including the structure of building bridges, smart cities, transport, risk management, and also the sensor system. Energy and power also have many applications and can be applied these computational engineering methods. Medical, of course, this is another area where it can be applied very fruitfully and usefully. And of course, autonomous robotics and intelligent mechatronics is an important area of digital engineering, where the recent developments we have seen are being also adopted or considered. So future direction, this area, engineering, like all any other system, will be also very digitalized more extensively, like our even home management, our fridge in the kitchen, our television, from the car to aeroplane, even all the sort of engineering research development and deployment and uses will become more digitalized in the future. So that is the future, and the we have discussed the recent the the developments which are taking place in that area. So if there is any time, I am happy to answer some questions, or otherwise people can send me an email or connect through LinkedIn.
Thank you so much, sir, for your gracious words. As we are short of time, the students can mail you the questions. Uh, questions है नहीं है. Very warm greetings, Professor Islam. How are you doing?
Fine, thank you.
Thank you. Thank you so much for being here today, again in the virtual mode though. But we look forward to meet you in person, and I'm sure the session was enriching for all our students. How was the session? Let me check with the students. Great. Please put your hands together for Professor Islam then. Yeah. Thank you. Thank you so much, Professor Islam, once again. And there is a lot to collaborate on, and we look forward to the opportunity when you can be here at our campus in person, and we can discuss further areas of collaboration, because I see you have been very active in different research publications and collaborative initiatives with other organizations. So we look forward similar collaborations with you, from Amity University side as well. Thank you so much once again for being here. Thank you.
Okay, thank you.
I think we are moving on to the question session, right? Okay, fine. Thank you. Thank you so much. Please, you have any questions, you can send an email to him. And he's very accessible. Please do connect to him on LinkedIn as well, right? And he'll revert to you with all your doubts that you have. Thank you once again. Next, we welcome Dr. Sandhya Samarsinghe, Professor and Head of the Complex System Big Data and Informatics Initiative at Lincoln University, New Zealand. Dr. Sandhya is a Fellow of the Modeling and Simulation Society of Australia and New Zealand and a senior member of IEEE, recognized for her exceptional contributions to advancing cutting edge methodologies for modeling complex systems. Her leadership of the complex system big data informatics initiatives demonstrate her commitment to utilizing the power of computational tools to address critical challenges in complex biological and environmental systems. She has joined us today to talk about auto-associative neural network for complex systems. May we now invite you to take over, please? Ma'am,
Can you hear me now?
Yes, ma'am. Yes.
Okay, that was a problem here. Sorry about that. So I think it's okay now. Yeah, thank you so much for this invitation. And I think this is my sixth or seventh time giving a keynote here. And if Natasha is there, hello. So today I'm going to talk about the photo associated to neural networks for modeling complex systems. And my background was initial engineering, and then I went to move to AI, and then I'm using engineering and AI in complex biological and environmental systems. So today I'm going to talk about this topic. So complex systems are, what are they? They are everywhere. If you look at the biological, ecological, environmental, political, and economic, they are very complex. Right? So complex systems are characterized by how do we know that, what are they, right? So many entities or nodes interacting in unique and complex ways. Like if you look at this picture here, you can see a complex system interacting very, very extensively. The people in the society interact, plants and animals in an ecosystem interacts, protein in cells interact to do functions, and chemicals in a reaction system. They are all complex systems. So they unfold over time. That means there's emergent system behavior like riots in a society or climate change in the environment or cell division in the biological system and so on. So they're nonlinear and complex, right? So it's not simple. Therefore, it's difficult to predict, the long-term behavior. And so the long-term behavior of these systems are typically characterized by the type of attractors. That means the final system state, right? Where do they end up, right? So it could be a fixed point stability. That means it stops. It functions for the period and it stops at a particular state, or it could be limit cycle where it repeats in cycles, or chaotic. That means there is no pattern, right? So how do we model these things? So one approach has been the mathematical models using ordinary differential equations. And what they do is that if for any entity in the system, every interaction between two things, they write an equation, write differential equation. And this is this says that P1, P2 interact with a particular rate K, and it produces a unit. So that's the kind of a one interaction, right? So it's common, but they require these parameters. And these are mostly unavailable for many systems like biological, environmental, and so on. So, but the nice thing is that they provide continuous behavior. That means you can track their behavior over time very, very closely. But challenging to deal with if you have large systems, these equations are challenged because a lot of big solutions need to be done, long time consuming, and so on. So the other side of things, the spectrum is the Boolean models, and they use binary logic, like if-then rules, to represent the interaction between two entities. For example, it says that if P1 and P2 are available, then the unit of Pi P2 will happen. Right? It's very simple, no parameters. So do not require parameters and easier to model for that reason, large systems. And also it's easier to explain the system behavior qualitatively because there's no quantitative values involved like here. This is all like a logical system, right? So therefore it's difficult to model the continuous behavior. So these are the two kind of spectrums, right? Two opposites. So now the problem that we are looking at is that currently there are no models that can represent the continuous behavior of complex systems without needing parameters. Right? So that was the problem. So we aim to fill this gap with neural networks. Why do we do that? So neural networks are, as you know, data-driven AI models, and the parameters are internally optimized from data. So they don't have to be given from outside. So that's the main reason. So this potential of AI has not been explored for complex systems yet. So we explore this in the context of biological systems, which are some of the most complex to understand and model. For example, cell division, how one cell becomes two in our bodies, for example, right? That's also other topic today, so I just put it as an example there. So the context is that biological system, if you look at them, the driving engine of the biological system is what we call protein interaction network, which is a complex system. So what is the protein interaction network? So let me talk briefly about what the proteins are, right? So this is not a biology lesson, but I'm going to talk just enough to understand the computing aspect, okay? So proteins, proteins are DNA products. You can see here the DNA, and this is the protein. You can see the cloud. This is the product of the DNA. So their proteins are ubiquitous in life. They carry out most functions in biological organisms, from breathing to cell division. And so anything in our body, anything, the proteins are behind that. So they are like intelligent agents with specific assigned tasks. Right? Just you can think of it as a node or some identity or entity, involved in our bodies. So proteins then form networks of communication in performing these functions. You can see here little dots. These circles are proteins and they interact with each other. So that's the protein network that's behind these functions, any function. So how do they communicate? Their function is to minimize the energy and minimize the overhead. It doesn't want a lot of clutter in the system. Their bodies can be huge, right? So it only uses what it needs. So that means the proteins, any of this here, activate other proteins that are needed for a particular function and only when it's needed. That's why the energy minimization, overhead minimization comes from. And these then when they are activated, they inhibit or degrade proteins that have already completed their task. That means when the job is done, they are cleared from the system. And then networks can also produce new proteins from the DNA as and when needed for a task. So this is, so we can see, it's a very dynamic network where things get degraded, things get activated, things get inhibited, and so on. And jobs get done in that way. So networks proceed this way until the goal of the protein system is achieved, for example, cell division. So it's a process, and at the end, there is an outcome like cell division. So now we can go talk about cell cycle and cell division. So if you look at this picture, cell cycle is a mechanism by which one cell becomes two identical cells in our bodies, plants, animals, and so on. So if you see this picture, you can see one cell dividing into two, right? So behind this system is huge number of proteins interacting in networks. So like I said, large number of proteins in the order of hundreds, and scientists are still uncovering some of the participants. Right? It's not it's not over yet. So we have these networks, and when in cell cycle, to do this division, cell accomplishes, these networks accomplishes 4 stages, right, of cell cycle. The cell grows in size in the G1 phase. You can see this cartoon here, G1. That's where the cell becomes bigger because now it needs, divide. It's going to be almost like create a new baby, right? So it grows bigger, and then in the S phase, DNA is copied or duplicated so that it has 2 copies, and the cell grows in size more in the G2 phase, so that it has more space for the 2 cells. And then there's another phase called M. Then the 2 DNA molecules are separated, and then 2 cells are formed. Right? So that's the 4 stages of cell cycle, and it starts with 1 and goes through the process, and there will be 2 at the end. So it's all done by these hundreds of proteins, and out of these there are 4 proteins. These are called cyclins D, E, A, B. They control each of those phases of this process. So these are like controllers of this process at each stage. So if you look at these hundreds of protein interactions, it takes about 24 hours to complete a cell division. I mean, one cell to become 2 cells needs about 24 hours. You can, this G1, SG2 here in some detail. But just to give you, just to show, what this means, you can, I'm not going to explain, no need to explain all these things, But these items, individual items, are like proteins. Like if you look at G1 phase, we have so many proteins interacting, and this is the cyclin I mentioned, right? This is only a simplified version. There are so many more proteins also in this part in this interaction. And if you go to the next phase, there's also similarly, a lot of other proteins interacting, and then the one cyclin is kind of looking after the process. And then if you go to the S phase, then there's also similarly a lot of proteins interact, and the cyclin A is more like the leader of that process. And then also if you go to the M phase, you can see cyclin B and so many other things controlling or participating with cyclin B. Right? So this is a very simplified version just to show you actually proteins are entities working together. So that's why we call it a complex system. So if you look at these four, these are the cell goes through one stage to the next, to the next, to the next, and the cyclins are the drivers of it. So these highlighted in yellow are the main controllers, and these are called key cell cycle protein markers. So they come cycling the first stage, and then the second stage E comes, then the A comes, and the B comes, and you can see the time course evolution of these proteins. So this is more like a process. It takes 24 hours. So our objective was to develop neural networks, so modeling these protein-protein interaction networks with the mammalian cell cycle. I showed you cell cycle, and using that as a case study, and also looking at cell cycle control system as an intelligent agent system. So what we did was we first wanted to do a proof of concept. So we extract the 11 most important proteins, that means the four cell cycle markers, those cyclins I mentioned, and there are 7 immediate regulators. So we want to start with a little bit in a smaller system first to study the concept. So we had 11 proteins interacting, and you can see the cyclins are these pink blobs, and their regulators are these yellow ones. Red means inhibition between two elements, and the black means activation between two elements. And you can see there's a lot of red here because cell cycle is very tightly controlled. Because if something goes wrong, there will be cancer. I'm sure you know about cancer. It's a cell cycle disease, right? And there are many other diseases that cell cycle can cause if something goes wrong in here. So the body actually controls this very, very tightly. So it's a very tightly driven control system. So we look at this core protein network, which we call core cell cycle system, and you use neural network. Now, there are some modeling challenges, as you know, with neural networks. So there are modeling challenges and there are data challenges. In terms of modeling, as you know, neural networks are called black box models. So question is, do they represent reality? And this is about medical, somebody's life. This is a life and death situation. So we want models that represent the real thing. So do they represent reality? And then we ask, how do we represent our system in a model architecture that is not a black box? I.e., we have one-to-one relationship between the model and the system, right? How do we do that? Then how do we model the unfolding of this network system over time? So system items come and go, and system progresses over time. How do we model that? And then we know that cell cycle is a limit cycle attractor. That means the system repeatedly go through some processes or the 4 stages every 24 hours until the desired number of cells are produced, right? So that's the modeling challenge. In the data challenge, high throughput protein concentration. That means you need to, if you have protein models, we want to know what's their level of the concentration, right? These measurements are gaining momentum, and the future will be data rich. But currently, protein data is still limited because of the cost of experiments and time-consuming experiments and so on. In many cases, protein data are binary for that reason. That means we know whether the protein is active at a time or inactive or on or off at a time. And these experiments are simpler, so we have some of this data in binary form. So we also use the neural network to address these data challenges. Now, in terms of model challenge, we were looking for some inspiration to have not a black box type architecture. So we we finally, settled on auto-associative neural networks for this, process cycle model. So what is auto-associative neural network? Where the inspiration? Well, this came from a model of C. elegans nervous system. This is where the inspiration. The C. elegans is a small, few millimeter long worm, and its connectome or the whole neuron system they have the neurons everywhere. This system has been mapped and it has been modeled, right? So how it was modeled is, just as the background of it, there is a network called Hopfield network, and this network, it's a dynamical system, right? It ecosystem evolves over time, and the unique thing about this is that there's a node system of nodes, interneurons interacting with each other, and every node is interacting with every other. You can see here it's a fully connected system. But you can see we don't have fully connected system, and even in this animal, it's not a fully connected. So, with Hopfield network, if you start with certain states, certain inputs, it processes information until it comes to a point, and that point has been a one fixed stable state. That means the system stops after some time, and that's the end point fixed state. So these researchers showed that actually we can even have partially connected like this to represent this system, and still system produce required stable state, different stability states. So they prove that it doesn't have to be always fully connected. Partially connected ones can be, or can have rich variety of behavior patterns. Right? So that means what they showed was the system unfolds in time and settles into variety of attractor patterns. So because this has partially connected, not fully connected system, and our system is also like that, and we thought this idea might work for our system as well, and that was the inspiration for our model. And for data, we have two types of data: the continuous and binary, right? So why do this continuous binary? Because future will be continuous. There's no question about it. But why we use binary is because at the moment a lot of data are in the binary form. So we want to give scientists different options, variety of options. So continuous. Then where did we get the continuous protein concentration data? Was from another model that we developed. It's a large 14 protein OD model of the same cell cycle, but it's a OD model of 40 protein. So it's not the perfect system, but we use the data. But in future, it will be tested on real data, right? So it has about 3,500 time points representing 24 hours, and this is a publication that we made. So from these 40 protein models, we extract the data for the 11 proteins. And here we use the 4 cyclins that I mentioned, and here cyclins and all these regulators, the 7 regulators. This is how the time evolution of these proteins, right, according to the model. And if you look at the actual data, it will look like here's the time, and here's the different values, they keep slowly changing and so on. So these are like numbers, right, concentration values. So for the binary the data with on-off proteins, for this also we use a data from a 11 protein Boolean model that we developed for cell cycle. Remember Boolean doesn't need parameters, so we had published this model also before, and this has the Boolean rules are providing, they provide 1010 kind of values for on-off kind of values for the entities. And here we have the 4 cyclins, and we also had data for the other 7 regulators that are shown here. So this has only 12 time points because everything is governed by a Boolean rule. So according to Boolean rule, it had only 12 states. So only 12 time points to complete the cell cycle. I'm just showing you what the data look like for the continuous model and what the data look like for the binary model. So this is our data situation with the models. For the models, there are 2 types. And so what do we do with this? So we looked at first developing whole system models, continuous continuous ANN models for the whole system. First, we tried with the linear activation functions for each of the neurons, and then also we looked at nonlinear activation function, especially the logistic, for each of these. So, two different full systems, whole system, that's one type of model. And then we also see, so we develop individual protein models and then assemble them into the whole system model. Reason is that the scientists are developing in finding new proteins and their characteristics, and they come in isolation. So idea was that if we have individual models, then we can, if we can assemble them, so we can, if in future you can add the protein as they are discovered. So we tried the linear protein models that each as individual one, each model is separate now, right? So linear models, then we have non-linear models, and then also you have binary using a perceptron model. So here the model is not like a whole system, just each one, each neuron, each protein is like a neuron with one of these functions, and then they can be added to it. Then we also had a third model, this hybrid one, the binary continuous. And then that is for what we call timescale separation. Why? The cyclings, the 4 cyclings I showed, they're actually slow. They take hours to, manifest. But their regulators are so fast, like light switches, right? So they are like binary. So we thought if we assemble binary for models for fast acting proteins and nonlinear ones for slow acting, then we can have a very realistic hybrid ANN model. So that's the modeling part. And then how do we train it? It's very simple. Protein is a neuron. It receives inputs. They can be activation or inhibitory from other proteins. You can see anywhere. Some are black, some are red. That means, different types of activation. So the neuron activation function is a continuous or linear or logistic and binary. Connection strength are the weights or the parameters, right? Like I said before, they are all individually, they are estimated from the data, right? So connection strength between the proteins are the parameters they are learned from data, and training is Hebbian learning, which is one of the earliest form of learning in neural networks. It basically says if a neuron activates another neuron, connection weights become them increases and vice versa. So that's a very simple idea. And then for each of those neurons, we calculate the activation, basically the weighted sum and the activation, and then the prediction error. Because we have the data, so we know that we can find the error based on the prediction, and then you update the weight using this error and the inputs, and with the learning rate. So this can be done whether it's a whole system model or individual models. This method can apply. So in the whole model case, all neurons update at the same time as a system, and individual model case they are separately trained. So results, I'm going to show you some results with that. So, like, remember I showed you the main problem with the neural network is that can they represent reality, right? So, my first question then we asked, can the ANN, we use the nonlinear sigmoid in this experiment, with a priori unspecified interaction pattern in the system, can it extract the correct pattern, interaction pattern, and produce the correct system dynamics? So what do you mean by that? It's quite loaded. Remember I showed you the interaction pattern is not very partial, right? Not each protein is connected to each and every one. So it's a specific pattern. So if you give the data set, can it find that specific pattern and then produce the correct protein behavior, meaning trend of the protein, the timing of appearance and disappearing of the protein and their concentration. So we tested this first, right? And then here are the results for the all 11. You can see here, all protein behavior is captured remarkably well by this one whole system, right? You can see that the dashed line is the predicted, and the solid line is the actual, right? Experimental or the given data. You can see most of them are extremely close, right? Very nice. So we were so happy. So it's a really good system. Then we looked at the weights. Remember this? Now the system had 11 11 nodes. So we had 11 by 11 weight matrix. And when we looked at this, we said, oh my God, it's a fully connected system. We don't want that. This is not what we are looking for, right? So closer look at the final weight matrix showed that the networks has a fully connected system now, not the required one. The required ones are shown in the board here, and everything else should have been zero, right? So now we see now that this is a real caution for all of us. Models may not always capture reality. If we give just the data set, it may give a different system back to us. So we realized that we had to just specify the system interaction and then train the models. Okay? So that's one lesson we learned. So now we go back to the other results with the ANN now with the specified connections now, and we use linear neuron system now. So the question now is, then can the ANN with linear activation function and the specified, that means the true connection pattern outside, give it from outside, they can capture the protein dynamics, right? So here what we see, the same system is now given to 11. For clarity, we are showing them in four graphs. There are 11 items here. But item here, you can see here that some of them are quite nicely like this blue. You can see the blue. And the blue are the cyclins, and they are reasonably well done, most of them, three of them. And some are, look at the brown one, there's very, the solid line and the dash line are so far apart. Even the green solid and dash line are so far apart. So some of them are good, some of them are not. So the red ones here at the bottom, we are looking at R square, which is the accuracy of prediction for these 11 elements. We can see the red ones are not the good ones, and the other ones are good. So some of them are really well represented, but some are really not so good, right? With the linear neuron system. So we are now seeing about nearly 50% of the system, including the three of the four cycling, the blue ones. Three of them are good, but the one is probably not good. At least nearly 50% are well represented. Some interactions are linear, therefore we can see why they are doing well. For some, is a linear neuron can represent them. It's a good finding. A simple model is enough for some of the protein interactions. However, some interactions are non-linear. That's why we cannot predict them. They need non-linear. So it's a kind of a discovery, and it's a kind of good finding. So now then we said, okay, let's go to nonlinear neuron system now. The ANN. So all the neurons are now sigmoid or the logistic, and now we see much better improvements, for all of them. Still not 100%, but solid and dash lines are very close to each other, and R squares are all in the 0.9, 0.8, that kind of range. So it's for biology, this is really, really good values. So our results now show that ANN6 with sigmoid can represent all protein interactions, linear as well as non-linear ones. So that's another finding that we had. And then now this is about system models. And then we look at, can we do individual protein models and then assemble them, right? That's one of the models. So now the question is, can individual proteins modeled by linear neurons capture the individual protein system, right? So now each one is a single model, right? One model for each neuron, so it separately. So when we did with linear ones, again, some of them were not properly modeled, but all the others were done well. But only two it had problems. But earlier with the whole linear system, there were more that were not modeled well. But when you do individually, there's even improvement there. So only two were not properly done. Then everything else had 0.9, 0.8, etc., 0.7. So now we see the individual, they can capture about 70% of the protein in the system. It's, like I said, more proteins than when we were linear system as a whole system. Right? So that's another finding. And then we look at going into, again, because not everything was captured well, we now ask, can the individual ones could be done by individual sigmoid neurons? And now we see all of them are very well modeled, and the R square is also very high range. So that means sigmoid can model all individual proteins, and that allows us to develop a modular development of the ANN as and when individual proteins are available. That means when the scientists find new proteins, we can model them separately and then assemble into the system. Right? So we assemble them into one system, ANN, and these are the results from these individual models. So that's very futuristic because it can be modularly expanded as time goes on. So now we look at the binary individual protein models. Like I said, we don't have data. A lot of times we have only binary data. So how can we do binary models, right? To represent binary data, and whether we can assemble into more like a binary ANN, right? So for limited cases, limited data case. So as you can see, we are kind of giving variety of types of models for the very different data types that scientists have. The question here is that can binary models capture individual protein dynamics? So binary data, like I showed you, remember we had only 12 time steps, small data set. But when we model here, they now complete ANN. Each neuron is a perceptron, 0, 1, right? And we trained using Hebbian. So we can see that all proteins are well represented with 0, 1 threshold kind of behavior. So we can see that binary neuron captures the on-off dynamics of all system proteins. Therefore, we could assemble them into the we develop the individual models and then assemble them into the whole system. So we can see that the binary models assemble into ANN with proper timing. We can see when it comes, when it goes, and so on. Boolean does not involve a time, so their timing can be wrong, but in our system, timing is correct. We compare with the actual timing of the cell cycle, and everything comes and goes at the right time. So we also refined this because only 12 times that we had, we thought, can we do a little bit more specific, a little bit more refined. So what we did was, remember we had 3,500 time steps for the continuous data, and we created the binary. So continuous data was converted to binary data into 0 and 1. That means if from the mean value above is 1, for a particular item and the mean value below is 0. So we have 0, 1 data set, but 3,500 time steps. So we develop again individual models for this data, and you can see the red and blue again are the target and the predictor. They're very good. And the blue is actual data from this converted data from the, continuous data from the ODE system. So we can see they all match completely, the ODE data and the converted data and the target data. So now we say the binary models follow the Boolean model and the ODE data very well. So that's also another finding. And then, last thing we want to ask was that can we develop models for timescale separation? That means, like I said, cyclins are slow acting, continuous, and the regulators are fast acting. They could be like binary. So it's a real system, it's a mix, not just one type, right? It can be two types now. Okay. So we developed nonlinear model for the 4 cyclins and binary models for their 7 regulators using that 3,500 time step data. And now we can see that the binary ones are here and the nonlinear, the cyclins are here, and they are also predicted very well according to the actual data is red, predicted is green. So you can see they are, so individual models are performing well. So now we can combine them into one system, which is a hybrid one, right? So that's what we did next. And now we have a binary and continuous individual protein models assembled well into the whole system. And now we see this, it's not binary anymore, not 0 and 1. So this one has going up to 4, 3.5, and this is going to 2. That means there's a continuous and continuous and binary both in the same system, coming and going at the right time and producing the correct system dynamics. Okay, so what we now can say is that in conclusion, the whole system ANN model can represent protein dynamics. We saw that. We also saw that AN with nonlinear neuron can represent all proteins, and about 50 in the system, about 50% of the proteins show linear behavior. That means we have very simple, some proteins are very simple. And if you look at the whole system, actually, the whole system is not terribly complex. Sigmoid can do, the patrilinear cannot do. So it's a kind of, nature has simplicity, but when they work together, it creates a lot of complexity. So we also develop individual protein models with nonlinear and binary to represent they can do. So the continuous behavior of all individual proteins can be modeled by nonlinear, and the binary also can do, models can do the binary behavior. That's useful for limited data cases. So these are the three systems three models that we looked at. And then we also found that individual protein models can be assembled into ANN. If it's a nonlinear, you can develop a nonlinear ANN. If it's a binary model, you can develop binary ANN by assembling, all this into one system. And then we showed that the individual models can facilitate hybrid ANN for time scale where some elements act fast and some elements are very slow. And that way we have one system where we have nonlinear and also the binary neurons operating, and they come at a particular right time, and they go at the right time, and some persist for some longer periods, like the full cycling, and the system takes care of all that. So that means ANN is a good way to address complexity and study the behavior of a full system. So I'd like to acknowledge my collaborators here, Dr. Thai and Koma. She's from India, my master's student, and Professor Don Kulisiri. And thank you very much for your attention.
Thank you so much, ma'am, for your gracious words. May I now invite the audience for questions?
Good afternoon, ma'am.
Yes.
Ma'am, I have a question.
Yes.
What role does the choice of hidden layer architecture play in the performance of an auto-associative neural networking?
Okay. So let me. That's the thing about the if you put hidden neuron, then we don't know what the relationship between hidden neuron and anything in our real system, right? So we are looking at more like a flat system. It doesn't have hidden neurons, but all if you have the system has say 20 proteins, it has 20 neurons. Each protein is represented by a single neuron. So it's a flat system. However, it goes through time, right? Every time, because it passes, neurons activate a protein activates another protein, and next time step, that protein may activate another protein, right? So it goes through time, but it's a flat system. It doesn't have hidden neuron. So we are always looking at the actual system as it is in real life. That's why we try to avoid the black box with hidden neurons. So it's a whole system. So if you have 1,000 proteins, we will have 1,000 interacting system evolving over time, and every time there will be something new in the system. Some, who communicates with whom will be new at different time steps, but it's a flat system. That answered the question. That's what the auto-associative neural networks are.
Any other questions? Okay, thank you so much.
Yeah, was it easy to understand?
Yes,
I
sir.
hope so. Thank you.
Thank you,
Any
ma'am.
more?
As we conclude, I, along with the entire IT department, send our sincere gratitude to all our distinguished speakers for sharing their time, knowledge, and expertise with us. This conference had been a celebration of innovation, research, excellence, and global collaboration, and making today a truly memorable and valuable event. Thank you so much.